ನಾನು ಹೋಗ್ಕನ್ಲ ಲಿಮಿಟ ಚಾರ್ಜ್ ಆಗಲಿ ಎಲ್ಲರೂ ಹೋಗೋದೈತೆ.
Hello.
Hello, hi.
Good evening, sir. Sir, just wait for two more minutes, sir.
Okay, sure. Thank you.
Yeah, sure, sir. Thank you. So, Prashant, sir, in the meeting, please mute your mic.
Yeah. Hi, ma'am. Shall we start?
Good evening, everyone. I welcome you all to this third day of faculty development program that is sponsored by ATAL. Today's first session is on breakthrough in LLMs, multimodal capabilities, and cross-domain learning. As a session speaker, we have with us Mr. Muhammad Karimullah. Mr. Muhammad Karimullah is a AI engineer and data science consultant with 9+ years of experience across academia and industry, specializing in machine learning, data engineering, and AI driven solutions. Proven track record in leading projects and building production ready AI ETL systems and mentoring teams. He currently serves as a senior data science consultant at Rubix Bangalore. He has designed and deployed AI-powered solutions for client use cases, including NLP-based automation and predictive modeling. It's so honored to have you with us, sir. A warm
Thank you.
welcome for the session. You can proceed with the session, sir.
Yeah. Thank you, ma'am. Thank you all. I welcome you all, guys, to this session on breakthroughs in LLMs, multimodal capabilities, and cross-domain learning. I'm delighted to be here and present my views and various things about these multimodal LLMs. What are multimodal LLMs and how they are being used and their evolution, the historical perspective, and the architecture behind them. So, and also we'll see some of the applications, how they can be used in not only we already know they are, we have RAG based system, retrieval augmented generation. We will also see few of the slides on how we can also use multimodal retrieval systems. Let's begin with the from starting, guys. Yeah. Hi. So as we can see the timeline of your the AI, basically in earlier days, it was more about rule-based systems. Then we went from rule-based systems to statistical methods, then machine learning era, basically from 2000 to 2010, or it might be a little more also. Then we have deep learning revolution where we used extensively the deep learning algorithms. So this is just a quick timeline on the earlier. So multimodal generative AI basically defines intelligent systems combination of various multimodalities. What do you mean by modalities? Modality here in the sense is audio, text, image, and of course video. So offers creative context aware systems where we can build systems which are can be used in various applications, and of course they are revolutionary in creating automations, creating agents, bots, and so on. So basically we see various lot of application across this. Visual LLMs are multimodal LLMs, so used by developers, AI, ML engineers, researchers, and basically more into automation side of things, because only text-based LLMs are not very good at doing more tasks. So visual LLMs or multimodal LLMs are much more effective. Text to image, video, image captioning, speech processing, cross-modal retrieval, chatbot development. These are the skills which are currently being asked for in the market. So various generative AI applications, speech recognition, computer vision, text to speech technologies, and various, as I told you, multimodal retrieval and search. Apart from your RAG, retrieval augmented search, we also have a multimodal search, which we will see. So you have, so till now we had chatbots, which are basically answering questions. Now, not only, chatbots are only dealing with the text, they are also dealing with the images and of course, audio as well. So just a quick brief about large language models. So large language models in earlier days were basically, they were single shot or few shot learning. Basically, you need not train them. If you just ask a question, you get answered it. Or few shot, you give few examples and you get the output from it. So basically, in a very general sense, if you talk about, in earlier LLMs were basically blind, and they were able to only deal with the text kind of data, and they were not able to initial stage. Of course, now not only text data they are able to deal with, but also they are able to deal with the visual side of things, audio side of things. So basically, just a quick overview about LLMs. So pre-training an LLM involves next word predictions. A pre-trained LLM can be fine-tuned for a specific domain, which are much more effective, and basically quantization, reducing, distilling out the large language models and designing, basically fine-tuning these models to specific use cases. So as we know, just a very general view on this, internet, books, and all these articles, raw, unlabeled data, trillions of data. We train these models, and these pre-trained LLMs, which have been trained on unlabeled data, they become a foundation models, and they are helpful in few short, multi-short capabilities and text completion. And further, if they are fine-tuned, they can work as classification, summarization, works as chatbots, RAG systems. They help RAG systems also. So a simplified depiction of a transformer architecture, because around 2017 is around the time when we had this the first paper. And transformer consisted of basically two parts, encoder and decoder. So encoder processes the input text and produces an embedding representation and numerical value out of it. So input the text, input text is prepared for the encoder. Encoder access this text into the encodings and returns and embeddings are put into decoder. So language translation was basically the initial application for this. So encoder segments basically involves bird-like LLMs, which are focused on masked work predictions, and these are basically encoding where we can create more embeddings out of it. So we have a lot of embedding models. Then we have decoder segments showcasing GPT-like LLMs, and basically which are generative AI-based applications. So initial GPT 3 was pre-trained on a data set which was 410 billion web crawl data and web text, books, and huge corpus of various kind of text data. So GPT architecture employs basically a decoder portion of original transformer designed for unidirectional, basically next word prediction kind of thing. So next word prediction probability is used, and immediately after each word, next word is getting predicted. So mental model of overall three main stages of coding an LLM basically involves data preparation, sampling, attention mechanism, and LLM architecture. So basically building an LLM, implement the data sampling, understand the basic mechanism, and once you pre-training, after you have that, a foundation model, and we evaluate the model, load these weights, and finally fine tune into a specific use cases or chatbots, personal assistants. So basically in GPT like decoder only transformers, input text is first broken into individual tokens. This is the fundamental things. So these words are broken into tokens and converted into token IDs and embeddings, and basically which are positional embeddings of similar size and resulting into embeddings that used as an input for LLM layers. So very general view of LLM, because we will focus more on visual LLMs. So majority of the current LLMs are generative pre-trained transformers. They are autoregressive in nature. They are very good at predicting the next token at a time based on the previous tokens, a bunch of previous tokens which we ask, which is basically a prompt. So future tokens are conditional on previously generated tokens, and then unsupervised training using the next token prediction, and basically probability distribution of a particular token. Every time we have a probability scores, and whichever has the highest probability score, which gets predicted and which value gets the rock. If you say that embedding lookup will give you which is the most asked, which is the most popular, which is the most highest probability token. So you can see here just a general example about this LLM. So timeline of pre-trained and fine-tuned LLMs. Basically, you have first paper on your transformer, then you had a bird model T5, GPT-3, and you can see as the evolution of these LLMs, we had lot of models. We had open source Bloom model, then we had multiple vision-based models started coming up. So currently we have from 2024 onwards, we have a lot of models like Olomo 2, Gemma 3, DeepSeek, Quen. We have a lot of vision-based models coming up, and they are being currently used into a lot of automation into the task, basically text processing, PDF processing. PDF processing is one of the challenging tasks from a computer vision and LLM perspective, because the data is the PDF is basically fundamentally not only the text data, the layout also matters. So it's very challenging that analyzing using this PDF layout, keeping the layout intact, if we should be able to extract this data and keeping the meaning intact. Basically, it's very challenging to extract data from tables. Of course, there are a lot of computer vision models like Granite, Lava, which are effective in analyzing and extracting the data, but still there is some lacuna, there is lagging behind in that stage also. So we had Chandra OCR, which is very popular, which became recently very popular, and also Quen virtual LLMs. So these LLMs were able to just take this data from the PDF and keep the tables intact, and also they are able to very effective in converting the text data, basically handwritten, of course, the very tabular kind of data, which was it was filled with manual words and all, into your into text, converting this and keeping the layout intact. Keeping the layout intact is one of the difficult, challenging tasks. And to build any application, we want to automate a lot of handwritten bills and all. And of course, when you want to convert this handwritten bills into the textual data and you want to keep the structure intact, we have a lot of forms still at the lower level, at admin level. We have handwritten tables, handwritten forms and all. And we want to extract the data from these handwritten form, handwritten tables and all, into converted them into a structured data. That will definitely help us. So coming back, this is just a brief intro about large language models. So basically, from a very general point of view, the earlier LLMs were basically completely text-based. They had only one mode was available, that is the text mode. They did not have vision thing, and they do not have, of course, audio thing also. Only visual. They can see only one perspective ahead. So if you want to build an AGI, or if you want to go ahead, definitely not only text is important, but also various other modes through which our LLMs can understand, because only understanding of text-based data is not at all effective in understanding the perspective, understanding of the overall world. So artificial systems that process multiple types of data, text, images, audio, video, and closely mimics humans is basically your multimodal AI. Single data point, single model is more of gives you a narrowed result. But if you have a text, image, and charts, we can use this multimodal AI and give you a better outcomes, better output. So text processing, NLP, natural language understanding, computer vision, image and video analysis, speech processing, converting audio into text, text to speech, multimodal fusion. Basically, now we have a text data, vision, computer, image data, speech data. Now we want to combine these different modes into a single mode, so that our LLM can understand it better and give a better results. So each you can have separate processing for each kind of data, each kind of mode, or you can combine these modes and extract key features. Are basically we can unify all these modes. These are some of the different applications. So basically a diagram representing that you are able to take the all data from different modes and get it inside the model. So the architecture of multimodal LLMs is also in such a way that you not only we there are different architecture where we have only text is kept separate, image is kept separate, audio is kept separate. Or in some cases we are interleaving, we are mixing the text and image. We will see as we go along in the PPT how we are combining the text images into a single embeddings. So you can see here, what do you think about the cat? Would be a good outfit for my cat. So basically we have an image, then we have a text, and we are trying to mix up the text and image. If it's there is an audio, of course, that, and get a response out of modes. So basically some images to tell you where we are able to ask a question about an image and evaluate from this multimodal LLMs. Different generation of evaluation, yes or no, or text generation out of the image when we give along with the prompt plus image, giving you a certain kind of output from this. So a few more examples, query an image and text. So different, we are combining an image, then text, and try to get an particular relevant answer. So let's have a look at history of multimodal LLMs. So this is a basic timeline. So you can see initially, first it's not here. Clip was basically the first attempt by GPT to create a multimodal solution, which was around 2021. Then we had different architectures coming up like Flamingo, which was based on cross attention, keeping the embeddings, text and image separate. And then we had Blip. Then as we went along, we had a Lava. Lava was basically an open source model, and it was also revolutionary in nature because it was open source and it was able to interpret from the image and generate text out of the image. And still people use, even in various companies, they use Lava to, whenever you have a PDF with them, we have an image. Lava is very popular because it can interpret basically any kind of thing from the basically describe an image, describe a table, describe anything. So Lava is more popular in terms of open source. Of course, proprietary models are still effective, but open source point of view, Lava is very effective in getting this. But as we go along, we have more models. So a lot of models. This is your overall timeline, and we'll go into much more into detail into this. So basically, we can say our LLMs were blind, right? So we were not able to see the image. They were not able to hear. They were, blind, and basically they were not able to see the image. So multimodal foundation around, in earlier days, we had statistical era, then transformer era, LSTM era. So basically initial days, we used a convolution neural network, ResNets, and train. We basically initial days, it was more about training and classification based algorithm, where we are able to classify basic, common example, dogs and cats, tigers and all different classification type algorithm. Basically these and CNNs and different in initial days when Jan LeCun presented his first CNN architecture, where he was able to classify the postal stamps into different identification of postal stamp. That was the initial architecture design. And after that, we had an RNN to predict next word. And here we are able to predict the next word. But, as the word text, the size of the text increases, they were not very effective and they were not able to perform well. LSTM still they were able to maintain the context. So basically, initial days, the fundamental of multimodal LLM images your CNN, basically features like vector, label, and conversion of training your convolution neural networks on multiple datas, multiple images, and labeled data. And once these images, once they are trained on these models, they were able to, these CNNs were able to classify the data into based on your, percentage of, softmax function, basically softmax function. What is the probability of that being a cat or a dog? So then we had, transformer in 2017, where Google introduced the transformer architecture, then which used the self-attention mechanism. So basically, to take a note, vision and language lived in separate spaces. You had, if you take a mental model out of it, you had a vision on one side, then you had a image on one side and the text on one side. They were not kind of interacting with each other directly to be saying that. So there was only thin interface, only limited joint reasoning was available. So the first revolution came up in 2021. So in 2021, OpenAI's CLIP model, it's contrastive language image training. So the full form is contrastive language image training, was the major breakthrough. It learned to it. The major breakthrough was it was able to associate an image with text. So you are trying to, of course, CNNs can do, but you need them on a particular set of data sets only. But here they were able to associate images with their text and description, and an image like cat. So again, there was the fundamental. We'll see more deeper into contrastive CLIP kind of model, which was the first of kind. So they were able to train an image encoder and text encoder. So the association between image and text embeddings. So it was trained on huge amount of data set, which was a caption data, and we'll see more into detail into the CLIP architecture. So basically, true pairs, whichever the image and the embeddings of image and embeddings of text, which were closer to each other, they were kind of similar and were pulled together, while dissimilar were pushed away. So it provided zero shot capabilities. You need not train them. Once the training is done, they are like, pre-trained kind of thing. So they provided zero shot classification and multi-shot also. So they still, they were not very general in nature. So let's see. Then we had a DALI, basically DALI in 2021. Not only these models, we were going towards the model which are able to understand the images, but also the models which are able to generate images. So for matching to talking. So now from association between images and text, we were going towards an where the images should be able to, the images should be able to
Understood now? You understood the concept. See, this is the big cloth.
Can you
And
just
from there you need to pick
mute
it.
yourself?
Hello.
It's not like, oh, it is
Hello,
three-dimensional.
Amrita ma'am.
Like that, we see the cloth also now. They are closing. You have seen the shops now where they roll the cloth. So if you open the cloth, it is not dress. If I have to cut, it will come only one part.
Hello.
So that does not mean that I'm going to make only back side. I have to make front side
Let's
also.
mute you.
ma'am.
So they will cut the cloth accordingly.
Ma'am, remove them from the
Madhavi, ma'am.
meeting, ma'am. Remove her from the meeting.
Can you just mute? I don't have the admin access. So yeah, sorry guys. So from association and captioning to, we went towards the description of a picture kind of thing, image and question. So visual, image question answering and image features, and but still these models and Flamingo was one of the in 2022, Flamingo developed by DeepMind showed the first time Flamingo was able to use at its base a large language model. So at the base there is an LLM. On top of it, we are able to train on the image, and finally we are able to link the vision encoder and able to describe the data. So the capabilities of LLM in clip kind of thing, we are not able to take the capabilities of LLM, but in Flamingo kind of architecture, we were able to take the core capabilities of LLM and able to use them. So basically, these also had some limitation. There was task-specific captioning only, and we were able to learn to inject visual context into text generator, but still the brain was separate. We can describe our brain as an LLM. So we have a brain. You can take an analogy of LLM as a brain. Now, if you take an LLM as a brain, the brain does not have eyes. So how to fix the eye? So basically, your first multimodal LLMs like GPT-V, GPT-4V, or GPT-4 with vision allowed users to upload images. That was the first time. And of course, Gemini 1.0 around 2023, Google introduced a Gemini built on multimodal capabilities. And of course, the open source, very popular model, Lava, LLAVA. Lava is an open source model, which was the first thing developed by open source researchers around 2023. So for the first time, we are giving our large language models eyes to connect with the external world. That's how the first thing began. Started from a strong pre-trained LLM. So at the base, you have either GPT or Llama style LLM, and you add something called as vision encoders to them. So we'll see more into detail in the upcoming slides. So add vision encoders and small projectors are connectors. So the architecture pattern was basically image converting into vision encoders, and we'll see they are different from their convolution neural network kind of vision encoders. We'll show you an image and show you in better way. So this was your token space. The LLM were able to understand and consume these visual information. So you're trying your the brain LLM, the foundation model now is able to see, and you're feeding your tokens into that, and we have different architectures on that, decoder only and your cross attention one. So we'll see more into detail that. So first time we are able to use the reasoning power of LLMs, integrate the image into there. So multimodal LLMs. Now current design space involved. The first thing is the backbone LLM. You can keep on changing the backbone LLM. Basically, the basic LLM, you can change it to Llama, you can change it to Quen, kind of the foundation models. You keep on changing and you try to input your image data into that. So that's how it keeps your so every combination, every foundation models you change. Basically, but you're not trying to train your foundation models from the scratch, but you're using your already built LLM models, and you're giving them, as the analogy I can say, giving the eyes. How do you give the eyes? Through the vision encoders, clip, siglip, and so many others kind of things. So you can change the LLMs, you can change the vision encoder. So this gives you a different kind of recipe. If you are trying to cook up a model, a vision multimodal model, you have the flexibility to change around the LLMs and vision encoders. And finally, how do you, of course, you need to integrate this text with an image. To do that, we have different methods, like how do you fuse the text and images? We have fundamentally decoder only, cross attention based, then you have hybrid. So basically, when you train a model, of course, we will use a loss function. The most popular of them is the contrastive loss. We'll speak about it much more detail. Generative grounding instructions. And of course, the most fundamental, what kind of data you are going to train it on, whether it's an web photos. So there are different open source data set, of course, data sets which are not available to general public also. So these are the 5 combinations. For every combination you change, you have a different architecture of your multimodal LLMs. Different model, different points. So each focus, some focus on documents, as we fine tune them, the specific use cases will differ and depending on the use case. So basically, if you want to have a mental model to this, how to see how do you want your LLM, which is the base model, how do you want to see it is your vision encoders. How do you want to fuse your LLM with your vision is your fusion architectures. Where do you want to put the eyes? And how do you want to train basically your loss function, training objectives, and the most important of all them is of course the data on which you train it. So this is your little bit of history, and we will dwell into this as we go along. So classic applications of multimodal LLMs is your image captioning, providing an input image and model generates a description of image. You can see an example around here. You have explained this meme. So because we have an image, the LLM is able to see the image, extract the parts of the image, and as the image goes to your LLM, it is able to understand the sarcasm. It's a sarcasm behind this meme, right? So it is able to describe the sarcasm and able to tell you what actually it means by this. And of course, because our image is behind the LLM, so as the image is given to LLM, it is able to reason and get the joke out of this meme. So, so as we know that multimodal LLMs are LLM-based models that receive and interpret and generate the multimodal data. So earlier multimodal LLMs were basically a clip-based. I told you, like contrastive kind of thing. So we have that maps images with text. The association between an image and a text to a shared embedding space. While generative models unify multimodal tasks into sequence to sequence formats. So we have been keep mentioning these models like Blip and Lava, the most important model of all, and the first of your first among the open source multimodalities. So the most common architecture used in these multimodal are decoder only architectures like your GPT, and Lava and InternVL is your decoder only GPT like architecture, which process the image within the LLM self-attention layer. Basically, and cross-attention based architectures where we don't combine these, we keep the images separately and text separately, and we input this cross attention. So image tokens are separate and text tokens are separate. We will go more into detail into that as we go along. So multimodals, basically fundamentally they are LLMs only, but on the top of this, they have ability to see. So instruction tuned LLMs serve as a universal task solvers to solve lot of tasks. There are a lot of instruct models. Instruct based models are very much important because on the top of any LLM which is instruction tuned, basically it is very easy for us to build agents out of it. So there are a lot of already in general LLM space, there are models which are general models, but there are models which are instruct kind of model. You will see that in those models, instruct models, they are very good at calling the APIs, reading through the functions of APIs. And here we are able to create MCP servers, MCP tools out of this, and function calling. Basically, the keyword is function calling. So your instruction tuned LLMs are able to call the function, use the tools which are available, whether it might be separate function callings or it might be in the form of MCP server. We have a lot of MCP tools hosted on it. So they are able to follow the instruction, call particular functions. So basically, any LLM instruct models they are very good at it. But of course, from an industry point of view, we not only want to read through the function, we want to also see through the function. That's what instruction following capabilities are very important even in the multimodal LLMs. So Vicuna, Llama, Chat, Mistral 7B, as we go along, we'll see through that. So fundamentally, multimodal LLMs typically use these pre-trained vision encoders called as CLIP to extract the visual features of image and video frames. These image encoders are trained on large text of data, and this allows for large scale training and training them, and various other types of data sets which are used for OCR kind of data sets. So some of the multimodal data sets which are available, and usually these LLMs are vision LLMs are multimodal LLMs are trained on. These are the different data sets. Some of them are open source. Vision plus text. They have vision plus audio, vision, audio, and text. These are different data sets on which usually we train our multimodal LLMs. So basically, any multimodal task they should be able to perform any kind of multimodal task, and models should be able to integrate this various modalities like image, text. So, and output of this you encoded data, then fused using strategy of fusion model, and it can be you can fuse it later, or now or later. You can delay that. So overall task of fusion model is to combine the representation of encoded data from unimodal models. So you can see here you have a different data coming up, and you have unimodals in the sense image is separate, text is separate, audio is separate, and you try to fuse them and give a joint feature space. So just an overview, text only AI, multimodal LLMs. So basically they are able to understand text and commands. Here they are able to understand all the modalities, and here generate response from text alone, while they are able to synthesize content across multiple modes. So operates under only text, but here they are able to operate even in the complex scenarios. So we require a structured prompt. Basically, you need a textual data only here, not only not text data also works. So enterprise level and real world applications, only text based LLMs are not effective, while multimodal LLMs are very effective. So performance varies, and they are cross domain. They are good for cross domain application. So just a simple application to understand how can we use this multimodal LLMs. Now, if you want to automate your invoice and contract processing, I see a lot of projects on this. People want to solve this. A lot of people are working on this. Now you see a lot of bills coming up, and they are of course not structured. You have manually written bills. You have a print out of that. You have manually written text on this. Now in this, the challenges is that you cannot use your normal OCR, right? Normal OCR would work well on your printed textual data, but that would not work well whenever you have a kind of handwritten tabular kind of images. So to solve this, there are so many vision models like layout LLM, donut, nugget. So they are able to parse these images in the PDF, parse these bills, and scan bills, scan PDFs, scan invoices which are signed or handwritten. The main challenge behind is keep the layout intact. The keyword is layout. Now, the biggest challenge is the layout, because a PDF has different layouts and the structure is also very complex. So basically, how can we solve these challenges? Basically, have a multimodal LLM on top of it. Extract these, use different vision models to extract the data, like vendor amount, tax, payments, handwritten bills, and validation, termination, and finally answer this text. This image data is converted into your embeddings, and your the foundation model is able to understand this text and able to answer your query. Customer support triage, you see a lot of applications nowadays. You have not only RAG based systems, self-help bots, self-help chatbots. You see in all the apps, we find those these kinds of chatbots. So whenever you go to an app, not only we want to have a text-based chat, we also want to, we have a delivery, and the delivery is there is a broken package, there is a broken, your parcel is, damaged and all, or there is a bill which is kind of, there is, expired product, expired food product. In such cases, your chatbots should not only be able to understand the textual form, they should be able to understand the image kind of data, because so whenever you have a expired product or some product which is not good enough, or there is some broken package, we should be able to take a screenshot and give it to your chatbot, and chatbot should be able to identify, is it really a broken, or is it it's somewhat manipulated or not. This is a very interesting use case. Classify the tickets into severity, what kind of ticket it is based on the customer image being sent to the chatbot, and accordingly raise the ticket and raise the concern. So it might be using an UI login page error, or something like, code is broken. Even in the code, people are trying multimodal LLMs, because every time we have lot of application, you write a lot of code, and similar kind of bugs may creep in, lot of bugs which are kind of similar, which is easy to troubleshoot, but you're not able to do it because the knowledge is getting accumulated, and people leaving the company, and the knowledge is lost forever. So we can document such kind of bugs or such kind of information, and keep it as an maybe in a RAG based approach, which is not very effective. Instead of that, we can keep them as image based learning, and retrieve it when the same problem occurs, same information is required, and it was solved earlier. So you can build an application where you have a damage, some kind of damage, in industrial, from an industry, there will be lot of, some similar kind of problems occurring multiple times. Now, every time you may have for that problem, you may have a different solution. Now, as the employees, lot of employees, very experienced, they know how to solve this problem. So we can label our images and with the solution. So this is broken, this is the solution. So we can create a knowledge pools. For example, in a maintenance industry, this part is broken, it means something, the solution is something else. So we can create an image and text. You have a broken element plus an text, how to solve it. And you can create an multimodal retrieval system where next time you need not require an expert. If you send a photo to your chatbot that this is broken, the chatbot will definitely give, because similar problem might have occurred 2 years ago, 1 year ago, maybe 6 months ago, and it will retrieve that image, try to man the image and retrieve the image, and also comes with the solution which was given by the expert, maybe 10 person with 10 years of experience. Now a people with 10 years, a new guy can definitely solve the same problem as good as the person with a 10 years of. So this thing is like it gives gives scope for lot of automation, and of course automation may have the bad side of it also, but of course more or less it creates a lot of automation, and people leave the company, but because we have this image and the solution caption stored in our multimodal database, it's not a simply retrieval kind of thing, it's image plus data, and this can be retrieved integrated with your multimodal LLMs to give a better answer. Even a new recruit can solve the problem in particular industry, or any kind of maintenance problem, or whatever it might be, by using this system. So lot of work is going on currently, and lot of engineers are working on these kind of solutions. Companies are trying to they don't want to lose the knowledge, they want to build an expert system from the current employees who have like 10-20 years of experience, and this information is stored into your databases, vector databases like Quadrant, VBIT, and we can even the employees may live, but you have their knowledge is kept intact. So this is one of the interesting aspects. Now, deep plot style vision model, that's one of the interesting kind of model here. So monitoring dashboard and charts. We can use charts like now we have a chart. I'll show you one of the example in the collab. So we can, if you want your chart to be, you have a graph, a complex graph, and you have a vision model like dplot, which can interpret what is the chart doing. Is there an increase in the graph or decrease in the graph? You give the screenshot of your dashboard, and the model will give you the interpretation out of it. Convert this visual plot into a numerical value or something like that. So answers the question. Did error rate spike in last 2 hours? Which region shows largest revenue drop? Summarize key anomalies in this dashboard. It is able to catch this kind of information. So this is some of the applications and the history. Let's go to the some of the architecture. As I told you repeatedly, I'm telling the club-based architecture 2021. As I told you, it was able to utilize the first model to utilize image, text, contrastive, objective. So a pre-training method involved to capture rich vision language and enable zero shot and multi-shot capabilities. So to enable the functionalities of vision models, you have contrastive. Basically, I'll show you the function also as we go along, and generative and alignment type. We'll discuss more into this with better diagrams. So existing research focuses on enhancing VLLMs, vision LLMs from three perspectives: large-scale information, image, text, designing effective models for learning big data, and designing pre-training methods for learning effective vision language correlation. So visual LLMs pre-training aims to train and virtual vision LLMs to learn image text correlation. What are the strategies for this? Translating images. You have an image. It's not like a convolution neural networks where every pixel is taken. We don't want to take every pixel. We want to take the part of image to emphasize the part of the image. So they are jointly trained, and you convert your image a part of image into token embeddings. I will show you the visual diagrams. It will be better for you to understand. And we fuse these parts of image into the language models, training images, treating images. The fundamental concept is word into embeddings. Instead of word, what we do is we convert image into embeddings or tokens. So vision. So this is the fundamental strategy. Instead of using the image, we are converting the image, parts of the image, into embeddings. To be careful, not like CNN. That's a different thing altogether. So smaller part of images converted into embeddings. So learning good image embeddings that can work on as a prefix for frozen or pre-trained large language models. So in this method, we don't change the large language. Repeatedly, I'm telling the same thing. You don't change the textual part, the fundamental foundation model. We are only adding eyes to the brain. Your large language model is your brain, and you are adding the vision capabilities to your brain, basically your large language models. So this thing is, these are the strategies. So first strategy is, convert image into embeddings, then learning image embeddings with language embeddings. Okay, you add these image to the language. So you're interweaving these things while your cross attention modules, which is kind of different, is flamingo style. I'll show you the image that will be easier for you to understand. So these are the strategies. One is here directly add an image to text embedding, image embedding to text embedding. Here, keep the image embedding separate, text embedding separate. So you are usually specially designed cross attention mechanism to fuse visual information into layers of language models. So for enhanced visual information across the model layers, we'll see more of it. So, yeah. So common, multimodal or vision LLM data set is you have MSCO contains 332 key images and each paired with 5 independent captions. There's a no caps designed to measure generalization of unseen classes. Then conceptual captions is basically 3 million pairs of image and captions align a noisy data set of over 1 billion image text pairs. Then you have LAION data set. So these are the data sets which are commonly used for training this, giving eyes to your large language models. So model families, I'll show you some code as well so that you can have a better. So these are your vision LLMs, visual question answering, visual reasoning, document visual question answering, image captioning, image textual data. So one by one we will go. So we will, yeah. Visual question answering is basically your kind of models where we give an image and we are able to give question and it is able to answer. So basically visual reasoning is also there. Is the dog in the air and the frisbee in the air. So the one of the most important of these is blip QA, is your blip vision question answering. It is a large pre-trained model for visual question answering. Like it's developed by Salesforce AI, which is bootstrapped with language image pre-training data set which leverages noisy web data. So it is trained on noisy web data and it was able to achieve state of art performance. So let me show you, if you go to Hugging Face, you will see a lot of, I hope you are able to see the screen, right? Shared. I have switched from PPT to this website. So visual document retrieval. If you go to Hugging Face, you have various multimodal tasks, any to any, text to text, document vision, question answering, visual document retrieval. So various, the categories of multimodal values. So we have one more here, the code with us. Let me go to the blip part. Can you see here? So here, as we told, yeah, it is developed by Salesforce. So just I'll not run this. It will take quite a lot of time. Already I have run this. So just import all these required libraries into your Colab. And of course, it's an open source. It will directly gets imported from your Hugging Face. So from the Hugging Face, I'm loading this visual question answering model called as by Salesforce Blip QA caption fit. Just I have downloaded this data set already. And once I download this data set, there is an image in my data. This is an elephant image. Let me go here. So I'm loading this Google Drive from Google Drive, my own Google Drive. I've mounted on the Colab and I have given the path to this. And this is your elephant image. So answering, is there an elephant? Basically, it is able to answer into yes or no. So top K retrieval, basically we can change it to 2 and do it. So I'm not able to do because it will take quite a lot of time for limited time session like this. So this is your blip QA. So yeah. Then you have a D plot. This is an interesting one. One shot visual language reasoning model trained on transplotting and graphs. So it's very good at understanding. Hello. Yeah. It's very good at understanding the graphs and plots, enables its integration with LLMs for question answering complex graphs, basically dplot. It achieves this by standardizing the plot graph and translation of task. So we will see one more example here. So this is my graph. Can you see here? This is a graph about countries, some economic data. Now here the same thing I'll do, just mounted my drive. And there is this graph located in this. What is the name of the graph? It is Google dplot. Okay. I think it is there in another site. Okay, it's there in outside this folder. No issues. Basically, this is the same data which I'm loading, and I'll just import the relevant libraries. And this is my pre-trained model, Google RT-plot, and I'll save it to directory. So as I load this image and load this model, basically load this model from the particular location and load an image. Now, this data is basically, this image is converted into a text kind of output. You can see this, it's a little bit, you can see countries, Germany, the values, Sweden, and the same image, and this individual responsibility, government responsibility. You can see the output being seen in the different formats, the responsibilities around here. This is your, it is able to catch the data from the images, graphs also. So this is your T-plot. Then VLT, Vision Language Transformer. It utilizes a transform architecture without convolution region supervision, fine-tuned on something called as VQA V2 data set for answering natural language question about the images. Basically, you give an image, you ask the question, it is able to answer this. So this is one more example. This is your image, okay, and this is your VILTQA question answering data, and load this data. And this is my image, which I got from directly from the HTTP request. So I've sent a request. I got this image out of it. It's about the 2 cats. So some data set, open source data sets. Just you ask a question, how many cats are there? Now this model is able to tell how many cats are there specifically. So this is about Vision Language Transformer or VLT data set. Then we have Layout LM. So it's an interesting one. It's a pre-trained neural network that understands the document images by jointly analyzing both text and its layout. Now, that's a very interesting application. Layout is, as I told you already, layout is a very interesting application, unlike your traditional NLP. So it is able to understand the font, size, position, proximity, in layout, the text location, font size, even the location of the text with respect to other text also matters. Now that's a very important application for understanding receipt analysis, document classification, making it powerful tool for extracting information from the scanned document. So this is my layout element. Can you see this is a quite a messed up application where you have somewhere printed application, handwritten one. Now this kind of layout here, definitely the layout is very, very important, right? So what we do is just from Hugging Face again, let's load this data set donut doc. So basically just load this. In this we ask the question, in which years did this guy ran for the senator's office? And we need to pre-process this image into a particular size, and we want this output to be captioned properly. And so when you ask this question, it is able to answer directly. It is 2016. Now, if you go back here, where is the name of the candidate? Anna M. Rivas. So it is actually, can we see the date here? Yeah, can see it is able to directly answer and tell you that it is 2016, right? So this is your layout LLM, able to understand the layout of the model. Then you have a donut LLM model, vision model. OCR free document understanding transformer. It's a state-of-art image processing model that bypasses, commonly whenever we want any vision capabilities, you want to convert image into text. The very obvious application is your optical OCR, optical character recognition. There are so many models. PyStrack. There's a track model. Then there is, Doctor, DOCTR. These are, a lot of open source libraries which are, you can use it for OCR. There's an easy OCR, which is very commonly used. You have a text, you convert it into, you have an image in the text form, screenshots, you convert it into text and use it. So it uses vision encoder, one particular kind of transformer called a swing transformer with text decoder bar to extract both text and image data. It is good in document classification, form understanding, visual question answering. Its unique strength lies in end-to-end nature, avoiding potential errors. And of course, we are not using OCR. Thank God for that. So without OCR also we are able to use that. That is your donut kind of LLM. We have NOGAT. NOUGAT. NOGAT is basically a visual transformer model trained on a huge number of academic papers, can directly read scanned PDFs, very good at understanding scanned PDF, even understand complex elements like math equations, optical OCR things. Yeah, so definitely anything to do with PDFs is definitely a good model. So you have NOGAT. Just again, I'm pulling up the model from the Hugging Face from this particular location, and this is your NOGAT paper. Here I have. Okay, I think this is a different location. So where is my VLLM? QA blip, yes. So this is my paper. So just one paper, which is PDF, which is a scanned PDF. I'll just put it in here. And we need to pre-process, convert it into RGB and process it a little bit and basically convert them into tokens. And you have this output of this paper into the textual form, right? So you can see this lot of things which are, next line is represented at /n, the formatting and all. But it looks quite intact, the formatting. Directly is able to read from the image. So yeah, coming back to the PPT. Then you have VIT-GP2, PyTorch model for generating image captioning built by combining vision transformer for a visual feature extraction, GPT-2 for text generation. Trained on CO dataset, it uses vision capabilities, vision transformer capabilities to convert. Same thing, guys. There's not much a difference as if you understand the fundamental thing, it's all repetition. You use an image to encoding data, text to encoding. Just you have language production to create accurate descriptive captions. I think this example is there. So you have basically your blip model, and here is your image, which is, so here I'll just load this blip image caption, the image, and this your blip image, which is this image is taken from directly from the HTTPS request response. Then we're able to process this data, and finally you can see the text output, which is able to describe. Our prompt is your photography of woman with her dog. Woman unconditional, woman sitting on the beach with dog and cell phone. I don't think there is a cell phone, but still it is hallucinating on that side, I guess, right? So then we have Git base, one more model. So this was the image, blip image, which I showed you just. State-of-art image captioning based blip, a framework for pre-trained on both clean and noisy data set. Okay. So it can filter out noisy caption, achieving improved performance and so on. Git base is by Microsoft. It's a version of generative image to text model. A transformer decoder trained to generate text description of the images. It takes both image and text tokens as input, predicting the next token on both image and previous text. It makes suitable tasks for image and video captioning. And this is again, okay, here we have Git base, and this is our image. And just I'm getting the image from the web, some kind of open source website. And you can see it is able to caption two cats sleeping on the blanket next to remote. So this is quite precise, it is able to even identify the remotes. It's able to section out the cats and able to locate the remotes. Yeah. We have one more model. I did not describe the clip model finally. So this is from that time we are describing about clip model. We'll go deeper and understand how the clip model behaves. So this is again, the same image given to the clip model. And you see, you can see we are captioning, trying to caption it. What is the probability of this being? Where is that code for me? Yeah, whether if we are asking this model whether it is a cat or is it a photo of dog. Now you can see here probability of this being a cat is 99%. Probability of this being a dog is 0.005% of almost none. So this is your clip-based model. Excels in image text retrieval and uses contrastive learning, which we'll see as we go along. Visual grounding. I think I have visual grounding example is not there. No issues. So dog is lying on a graph, face grounding, and referring the expression and comprehension. So this is it draws a bounding boxes and tries to implement, like interpret it. Image plus text output bounding boxes. So then we have OWL-VIT. This is is a powerful object detection model built on standard vision transformers. It excels at open vocabulary detection. It can identify objects not present in the training dataset. Even if your model is not trained on a particular thing, it is even able to generalize and give you the output of this. So this is your OWL-VIT model. So this is your model which I'm loading. And this is basically an image. What kind of image is this? You can just put it up here and see that. So this is same image. Okay. The same image I'm loading and asking it whether it is a photo of dog or cat. And just you can see the confidence with it is cat is 70.7%. And you can see the location of this. Even you're able to tell the location by kind of bounding boxes and the location of the second cat also. This is your quite effective model. So grounding DNO. Okay, we don't have grounding DNO example. So one more model which combines text and image backbones. So you go through. So then we have auto-regressive model. These models treats tasks like translating text description into sequence of images tokens, and they use encoder decoder architecture. Then you have stable diffusion uses latest diffusion technique where it builds images from noise and progressively guided by the text prompt. And fundamentally at the base level, it uses frozen clip model and it's a light architecture. So this is your stable diffusion. I think we have this example somewhere around here. So this is your few more clip models. So it is able to identify zero shot learning. I think we have it. Same thing. Okay, here we have diffusion model. So this is your diffusion model, stable diffusion. Just now I showed it here, right? So this is your diffusion model, which is clip. It uses clip and encoders, and it is able to convert text into image data. Now you have this model getting downloaded. And what is my prompt here? I have used CUDA freely from my collab. So an astronaut riding a unicorn ultra detailed 4K. Now this is my prompt. Now I want to save this in this location. And when I run this model, it will take quite a bit of time, guys. So you can see I've already done it for you. So this is your, astronaut riding this. This is done by your stable diffusion model. Basically, you run. It takes quite a bit of time, but it's slow. Yeah. So you have pre-trained vision language pre-trained models. Use the path of image, then use text, merge them, and pre-training objective, mask language embeddings, various kinds of training. So some of the visuals to make you understand in a better way. Text encoders, visual, we combine that. Then we have various other things. So let's focus on something like before clip, the vision technology, the transformers were different, especially on the clip. So before clip, it was multimodal deep learning, deep visual semantic alignment, neural captioning, use of CNNs, RNNs, and aligning of text with image regions. This was the structure around 2011, 15, and so on. And after you had a clip model coming up by 2021. So it was a game changer, learning from the vast internet text image space, and further innovations and modifications of group VIT blip. So these are the different modifications of your your clip models. So contrastive language. So it uses vision encoders, converts images into embeddings using vision transformer. And your text encoder, of course, it converts it into embeddings from text. So we have, yeah. So basically, the main concept behind the clip is that contrastive learning it's an unsupervised deep learning method aimed at when this clip model gets trained on a huge amount of data, we want to close up the distance. Basically, we want to reduce the distance between the image and the text. The objective is to develop a representation where similar things are, the distance between the similar things is brought nearer. So this embedding of this image should be closer to this image, while the embedding of this image should be farther away. So during training, similar text and the images, and of course the multiple images are brought closer together. So basically your contrastive loss is the fundamental thing. So you want to reduce the loss, minimize the loss, the distance between those things. So that is the fundamental. Pull in, bring similar images closer, and dissimilar images further. So this is how the concept of architecture allows the clip to adopt variety of visual classification benchmarks. It does so by simply receiving the names of visual categories, recognizing, demonstrating zero shot learning capabilities. So contrastive pre-training, basically you have an image, you have a text. This has a separate embedding. So clip computes the dense cosine similarity. You have a vector of text, we have a vector of image, and these two vectors are kind of, a clip is able to calculate the cosine similarity between these image and the text within the batch. The core idea is to maximize the similarity between correct pairs and minimize the similarity between incorrect pairs. This is your contrastive. So if you look at this contrastive pre-training, text encoder, image encoder, bring them to closer together. So huge amount of data. You have a text, you have an image. You try to take this up and try to build an this thing. So clips features independent encoders allowing flexibility of choice. You can choose resonate behind the scenes, and clip has shot image classification, diffusion model conditioning, and similarity search. So this is your capability of clip. Now clip is trained on 40 million images text pairing gathered from the internet. Because it is by GP2, this text data is not, it is not open source data. They have, it's not publicly available data set. It's a specialized data set, which is owned by OpenAI. And this data set has, partially text and partial, the text or captions are partial in nature. And largest resonance based clip trained models took about 18 days on 592 V100 GPU, and largest, fundamentally they used ResNet. Here they used Vision Transformers clip. It took about 12 days on 256 V100 GPUs. So this is your training data of clip, and this is your basically your different ways we have used. So to better understand this, you have a vision encoder, convert into embedding, text, convert into embedding. Okay. Encode image into vector, text into vector. Now what will be the next step? So high similarity. Wherever there is a high similarity between the image and the text, you bring them near. Now what is the loss function? So this is your cosine similarity. And move away, push away the images and the text which are not similar, low similarity pair. So contrastive learning embeddings, image and text similarity. Maximize the similarity between image and the text and its a caption, and minimize the similarity between image and other caption which are not similar. So it's like a multi-dimensional space. Maximize the similarity, minimize the dissimilarity. So this is your, again, the training loss. So you need to minimize this error or loss function. This is your loss function. Vision transformer, resonate based. So the vector size is 512 and 12 layer 8 attention head GP2 to its dimension space is 512. So parameters of both encoders are adjusted so that matching image text pairs having higher similarity scores, they are brought together while some are pushed together. Clip architecture training, no pre-trained weights from ImageNet or NLP models. Large mini batch size data. Basically, we have trained this model in the batch size of 332,768 and distributed training across GPUs. And predicting captions for word for word, different captioning, and try to minimize the loss. So aligning, matching text and image, generate synthetic data. So these are the various things about things, basically your clip model. So there is one more model like clip. You have Align by Google. Basically the same thing. It learns joint image text and embeddings from large noisy data set. The data set used is different compared to your clip. So of course the capabilities of this Align model by Google will also be slightly different. So clip limitations, struggles with counting the objects, determining the distances, has difficulty distinguishing subcategories, basically it is able to identify the bird, but not able to identify the species of a bird, dog, but not able to specify the species of dog, car, but not able to identify the car model. So out of distribution edge cases, biases from uncurated web data. Of course, there is ethical issues. This is your model card for this and vision encoders, January 2021. So it has a bunch of limitations. So, we can compare this. This blip is your generative model, while this is your aligning kind of model. So we'll go because we have less time. So we'll go to more. So Blip combines both vision encoders and multimodal mixture. Vision transformers are able to divide the image into small parts and have multiple models. I'll just quickly brief through. So you have target data set, train this, pre-train, and fine-tune it later on. Okay. So these are the various transfer learning applications. Cross attention layers. These layers enables model to dynamically focus on the relevant aspects of one modality. So just I'll quickly go ahead and we'll just quickly go to the one more important topic around here. So, this is one more thing, just because we have lack of time, we'll just cover this up. So method A, you have unified embedding decoder architecture and cross modality attention architecture. So these are the two fundamental architectures where in this case, we have an image, apply an image, encoder and projection, image patch embeddings. We convert the image into embeddings, then we have a text into embeddings. Everything is on the same level, and image and text both are passed into this GPT-like LLM. While cross-modality attention architecture is where we keep text separately, image separately. So we separately send the image, and this is the most important fundamental classification which we can understand. One is your unified embedding decoder architecture. One more is cross modality attention architecture. These are the two architectures. So here in this unified embedding decoder architecture, we combine the image and text, but in the cross attention, we keep them separately. So this is your image, unified image decoder architecture, single decoder model, like GP2 or Llama 2. Images are converted into token, text is converted into token, and they are both concatenated. So this is your decoder only LLM. Example, the most famous LLM for this is Lava and Quen VLM. Then you have decoder only multimodals. Same thing, same example we can say. So, Quen, there is some difference in this decoder only also. They use something called a simple projector. Now, how do you join this text with images using this simple projector? So Quen basically shrinks the image data into more efficient form and is able to train. So basically in the recipe of training the model, every time they are trying to change something, optimize something. So what do you mean by this? Connect the eyes to brain. Already I mentioned about that. Cross attention based MLM. They treat the images like a foreign language. I told you, right? Separately, image is separate, text is separate, and you bring them together. Model uses cross attention layers to process the flattened image tokens, unlike decoder only models. Flamingo is built on the top of frozen pre-trained LLMs. So Flamingo is one of the important models. So depending on what kind of model, the performance also will change. Okay. So if you compare them, decoder is, decoder only, where you combine the text and image is simplified, while cross attention, which is an example, is Flamingo, where you try to keep image and text separate. It's little complex. Includes all image tokens, but here short image tokens, they stay separate. Slower with high resolution, can handle high resolution because they are separate. This is your cross models, keeping the image separate, text separate. So basically you have, this is some kind of image representation. So vision transformer, one more concept which I should cover quickly is that in vision transformer, you convert the image into small parts and use this vision kind of thing. Image tokenization, you use something called as projector. So whenever you want to integrate this image inside your model, we use this projector kind of thing, while text tokenization is fairly simple. So you take these images and use linear projection and use this model. So basically linear projection module is used. We want to convert this using after vision transform, you have pieces of image, you pass it inside them. Then you have unified embedding decoder. So finally you combine this together, image embeddings using the projector and join them together. So this is your architecture of your vision encoders and your cross attention using multimodal cross attention. Just I'm skipping through some of the slides which are can be because of shortage of time. So basically, easier to train, more complex. So overview of different components of LLM. So basically, you are bringing the image separately. If you put the image with text, this is your unified. If you send the image separately, it becomes a cross-modal attention architecture. So just how can we choose? There are different ways we can choose this LLM. So just I'll go to the most important part. Modern multi-language, multimodal language models. Basically, you have here you can see different Llama 3V, which the base model is Llama, while vision encoders architecture is unified decoder only, general purpose LLM. Thus, you have MOL, BIT. The base model is their own OLMO model. Quen VL, base is Quen 2, Mistral for Pixtral, and you see different vision encoders they are using. And here you have different architecture. Now, fundamentally, you see, this is very interesting model because it uses mixture of experts. Pixtral and ARIA uses this mixture of experts during inferencing. The cost of inferencing and training is reduced. So this is a unique, in a recent thing. This is something special about these models. While these are normally are kind of not much differences there. Llama 3, which is a pre-trained model, it has used clip-based architecture. So just let me quickly go through this. This is your architecture of Llama 3. It keeps text separate, images separate. Can you see here? Text is separate, images separate. Then multimodal open language model, MOLMO. So it is one of the open source model. Then you have it uses different architecture. Now, the interesting thing about it overlaps the image so that the training happens fast. I'm just going through quickly because it is times is almost up. You have in the models also you have open source model, you have open weights model, closed model. So what is the difference between open source and open weights? You have open source, truly open source model will have code and weights downloadable, while your open weights model, basically train and weights are downloadable, but the code and the recipe for training the model is not available. While your API only closed models are basically your black box models. I can see in MOLOMO model, there are different variants. These are all open source, open weights, open code, everything is open source. But you see, in VLLMs, everything is open. While LLM backbone, some parts are not shared. Vision encoder part, some parts the code data is not shared. And of course, these are your completely API models. You don't have any access to that. Then you have open weights model. They don't reveal their data and all. But of course, you are free to download this. And open weights, you can train them accordingly. So then you have a bunch of open weights data model. You have Lava, the very popular one. And these are your different models. Yeah, guys. I think that's all, guys. Because of shortage of time, I will conclude on this at currently. Now, if you have any doubts or something, you can free to share and connect with me. I'm really thankful to the organizers and team who are working hard to organize this. Thank you, everyone. If you have any doubts, you can just ask the question in the chat. We have a next session coming up. Just I'll conclude here, guys. Yeah.
Any questions from the participants?
Yeah, you can put up in the chat also, I guess.
If any questions, you can put in the chat box. I hope there are no questions, sir. Thank you
Yeah,
so much,
thank
sir. That was
thank you.
a very informative session. Thank you so much for being with us. We are much obliged, sir. Thank you so much.
Thank you.
Participants, kindly be online. Tanish, sir, you're there. Are you ready for the presentation? Sir, am I audible? Sir, you are on mute. Hello?
Am I audible now?
Yes, sir, you're audible.
You're audible.
If you're
Yeah, just
ready, we
audio
can
settings.
start with the session, sir. You're ready, right?
Yeah, I'm ready.
Yes, sir. 2 minutes.
Yeah.
Yes. It's time to start with our next session on fine tuning and transfer learning, customizing models for specific tasks. For this, today we have Mr. Tanish Kandar as our session speaker. Mr. Tanish Kandar, he is a design and development enthusiast with analytical and problem solving mindset with passion for automobiles and data. He is into developing digital and machine learning solution, and also he has a strong and a practical math and statistical foundation, and he has ample of experience with Python programming and handling databases. He is proficient in data science, and also he is a professional data science and AIML trainer. It's so honored to have you with us, sir. Warm welcome to you for the session. You can take over the session now.
Right. Just making sure one more time that I'm audible.
Yes, sir. You're audible.
Okay. Thank you so much for the warm welcome. Thank you so much for the sweet words. Means really a lot for me. Being here in this platform, it's really nice to be on the other side of the table. So it's really an honor for me actually to be here and to be able to present whatever that I have learned, realized, explored for that matter in the past couple of years, ever since these things have been handed over to us, right? Because it was the LLMs, the AI era, ever since, the only reason that it has been able to grow is that, majority of the things which were kept unconfidential, so that people could explore and, they could really leverage it. So, um, I find myself one of the very few people, right, those who have not really understood a lot, but explored a lot and really use things to get the clear idea end to end. And that's what I do to all my students and mentor them and whomsoever I come across. So that's exactly what we would be doing here. The introduction has already been given. Myself Tanishk, as you all know, I speak English, Hindi, Marathi, Tamil. So if you have any doubts and you don't feel free, you can just ask me doubts with any language for that matter. We will be focusing on LLMs for that matter, but transfer learning is a quite general topic. But we'll try to categorize everything. We'll try to get a clear idea of everything, and as introduced, we'll be getting into the maths of it also. So we'll be getting into the dirty maths. We'll be getting into the derivatives, how things are going on, what is freezing and freezing, how the knowledge is really being transferred, what exactly is knowledge, right? And what is fine tuning really? We are going getting into all the things. Okay, so just give me 1 second. I'm setting up something here, and let me share my screen. I'm new to this Microsoft Teams actually. Quite okay. So here's the share button. Just give me 1 second. So I hope you are able to see my screen.
Yes, sir.
And yeah. So at this point over here, you can see my Google Colab notebook. So I thought before we get into any understanding for that matter, it would be nice that we start with the practical example, right? So in this session, there is going to be code for the practical purposes. There is going to be a lot of theory for the conceptual purposes. There is going to be a lot of explanation, and then there's going to be a lot of understanding going on. So this is the first phase I would like to set up over here. So let me just quickly introduce this code to you, what's really happening in the middle of all of this mumbo jumbo and all of these errors and everything. Because these codes take a lot of time to run, I am already running this code from past half an hour so that we can save a lot of time over here. And as you can see that I'm almost there. So let me give you a little bit of context what's happening here. As the session that we are going to see over here, I wanted it to be really practical and for you guys to be able to really do it on your own hands-on, right? So I've come up with this Google Notebook. If there is some way, I will at the end of the day, at the end of the session, I will as well share it with the organizer, so that this drive will be distributed to all of you, and you can all code along and run this in your own local machines and see what's happening. For a very short introduction, fine tuning is not a cheap thing in terms of computation. It takes a lot of RAM power, right? It takes a lot of GPU power. And from someone who is already doing this from years, I knew what exact machine that I wanted. So I do have a powerful laptop at this point, which has, to be specific, it has 32 gigs of RAM and it has a NVIDIA GPU of 8 GB, which is NVIDIA 3080, if I'm not wrong, right? And then it has a processor, which is i7 13th generation. So those who are looking for the exact specifications, this is like the least that you can go with, because for me, it has been comfortable. All right. So, and it is obvious that majority of the people will not have such specifications. So it is something that won't prevent you. Okay, we are living in 2025, moving to 2026. So advance happy new year to all of you anyways, right? And we are having a lot of resources available just like that. Okay, it's for free for us. So this is Google Colab for those who don't know. Okay, this is notebook architecture coding code editor, where you can write your code in cell and you can run each cell as your code. Okay, and this doesn't run on your laptop, so all you need is just a browser. I'm using Microsoft Edge. You can use your Google Chrome, Brave. Feel free to use whatsoever that you have. Okay, so you will be just going to the link that I've shared you. You'll be downloading this folder, uploading it to your own drive, and then just running it. Okay, so it should get you to the Google Colab. And if you're finding any difficulty running the Google Colab, you can just go through any YouTube video of how to set up Google Colab, and you should be able to fire it up. Okay. Now in this Google Colab, okay, we have provided you a data. Okay, so you will be given this data. This is a JSON format data. JSON is nothing but dictionaries nested into each other. Once we move to the slide part, I'll be drawing everything and explaining it to you, so you don't have to worry about it, right? At this point, I'm just importing a JSON library, which will help me to work with the JSON data, which I have created with DeepSeek. So it's not something that I script. Okay, you can just use a LLM to fine tune another LLM, right? So that's how simple we have to keep things up. Okay, so that is a file that you have to download. So you can see that JSON extraction dataset of 500 examples. It's a JSON file, as you can see. With the read mode, you're going to open it using the JSON.load function, and you're going to store it in a variable called file. Okay, so I have already run a few cells, so I'm not going to run any cell again. Okay, but this is how the output looks like. I'm going to explain you each and every cell, each and every part of code, so you can just, when you just copy paste it, you are not into an existential crisis of how things are working. You'll have an idea. In this examples, you have a format which has been followed carry forwardly, which has been followed thoroughly, right? So this data set is a replication of what might have gone into the actual training process of LLMs. Okay, so what I'm trying to say over here is that when we scrape the data from internet, right? So this is the word. Okay, I'm pretty sure that this is the day 3 or 4, right? So you must have come across a lot of terms of what the LLM architecture is, how the data was given to it, feed it to it. Okay, how it was extracted, how it was prepared. So if not, this is just a brief intro of how things go. Okay, so it takes a really lot of data. Okay, now in our recent models, we are talking about petabytes of data, right? So that's roughly around 175 trillion words. Okay, so that's the scale of data that we're talking about. And where do we get this data, right? So during the time of research in 2018s, 19s, 20s, 21s, right? They collected a lot of data from Wikipedia because it's open source, right? I mean, it's available, right? It's available to us. It's to us. We don't have to pay. There's a lot of text out there. It has everything. It has history. It has science. It has every topic that you would come across in your life. It's like the internet dictionary for everything, isn't it? So it has the explanation of everything, and that is the best data that we can talk about. Okay. And if you haven't understood so far what LLM really is, right? It is just an autocomplete model. Okay, so it's really nice to see. It's really it really amazes me to see that all the way the AI scape of all the way from completing the word that we are writing, right? All the way to the I see a hand raised. Is there any question? Do we have a question?
Yes.
Yeah.
Can you share the link of your notebook so that we can follow it along?
I can sure do that. Who's the organizer here? Is it possible for me to share this to you, like link in chat or something?
Yes, you can share it directly in the chat, please.
Hold on. So this is the drive folder. Make sure, guys, that you download these folders because I'm the owner. So you'll get the errors over here. So all you have to do is just download these things, right, in your local machine, and then those files you upload in your drive, and then just double click on this particular file. Okay. So that's the idea. I'm just gonna copy this. But it will be available for you. Yeah, I guess it will be. Chat. Where's the chat? I'm leaving it in chat actually. See people if you can access it. Let me know. We won't waste much time over here. If in a minute or so you are able to access, that's great. We'll be able to follow along. If not, I'll give a detailed
Sorry,
instruction to the organizer, so it will be shared with you.
can you
Yeah.
share the shareable link so that because it is asking for request from your side?
Request, yeah. So one person has to send the request to me. I'll give the access, and
I
then
I
it has
did
to be
that.
carry forwarded. You did
Yeah,
that,
I
okay?
did that.
My internet is lagging a little. I hope I'm audible. So I have Swiggy messages for some reason. I haven't received your message. Okay. So okay. So what we'll do is, I hope you can see the screen, right? I hope you can see the Google Colab, right? Guys, can one of you unmute and say?
Yes, yes.
Yes.
We can.
Okay. So what I'll do is I'll just have a word with organizer once the meeting is over. Okay. So at this point, I would want all of you to just follow along with me. Just understand the entire code. It is a highly practical and easy to understand code, and I'll try my best to explain everything to you, right? And I will share the access with the organizer, and we will let them create a send a request to you, and so that I can accept all. So I guess that's what we will do. I hope audience you can understand that, right? So we have already limited amount of time for such a massive topic, right? And I don't want to skip anything basically. So that's the entire idea. But if that's a deal breaker request, we'll surely look into it. Okay. So I hope you get the idea. 1 second. I was able to see the chat until now. Now I'm not. Give me 1 second, guys. Let me stop share and share again. Okay, perfect. This looks good. Right. Okay. So as I was talking, it's really amazing to see, right, from a technology which was just meant to complete the word that you're trying to, write. So if you're able to write, data, so it's supposed to predict science. Then all the way we started predicting the next few words, and now we are able to, generate text on our own, which in offline sense, right? So it's really, really crazy how things have moved forward, and I really think that we should, utilize this in our day-to-day life also. Okay, how do we use this in our day-to-day life? That's completely subjective, because applications like ChatGPT is not a, it's not a model, right? It's an application. So it already provides you a transfer learning technique, which is RAG. So a very big, technology. They have built a automated pipeline over here. All you have to do is just put some PDFs in your chat, right? You do it, right? So in ChatGPT, you go, you put the PDFs, it understands the entire context, and now you can talk to your PDF, right? You're able to do that. So that's the entire concept of RAG. So one very big, use case of RAG, they have already made it accessible to all of you, right? So that is for sure that you can go ahead and utilize that. But another part which is not technically that easy to implement and not something that everyone would want is transfer learning and fine tuning an LLM based upon your not touching the entire model itself, right? That is not something that RAG does. That is not something that ChatGPT does. Okay, so that is something that we are doing it here, right? So all you have done is got this data. Okay, this is the code that will be running for the first time once you get this notebook. So this is nothing but Google's library, which has this notebook called Colab. Okay, and you're going to import the drive function, which will help you to connect your drive content, right? So you're gonna run this drive.mount. Okay, and this is the path where your content would be. Okay, you don't have to change it, you don't have to do anything. All you have to do is, just as soon as you get the notebook, just click on run this cell. Okay, and you should get this message mounted at content / drive. As soon as you are able to see that, you are good to go. Okay, you can remove this line, but it's okay, you don't remove this line. Okay, you keep both the lines actually. So what you're essentially doing over here is that if you get this notebook from my side, and if I have installed Unslot for you already, you're going to uninstall that, and you're going to install Unslot, TRL, PEFT, Accelerator, and Bits and Bits. Okay, these are the libraries that we are going to utilize in the process of fine tuning an LLM based upon the data that we had. Okay, so you're going to install all of these libraries, and mind you, this is going to take roughly 3 to 4 minutes. Okay, based upon your internet connection and everything. So as you can see that it's gonna uninstall and install and set up a lot of stuff. Okay, so if it is able to show the runtime somewhere, it should show that it took me around 3 minutes somewhat seconds, but that's okay. So it is completely fine if it is taking very long for you. Do not refresh anything, do not close any tab or something. Just give it its own sweet time, right? And it's going to be perfectly fine, and it's going to be set up, right? One more thing, guys, the reason why we are using Google Colab is that we want to use the computational power, right? Which your laptop does not have. So make sure that you go to this part of your Google Colab, and you make sure that runtime type is set to T4 GPU. So it's a Tesla GPU. Okay, and you set the Python 3 as your programming language. Okay, and you hit the save button, right? And as soon as you do that, you can also run this particular piece of code, right? Which I got error over here. That's why I was not going to touch this entire file only. I guess this part alone. Okay, this I'll just remove this thing. Right, so basically, as you can see over here, that now let me add that comment so that you can understand what was happening here. So just hashtag, I'm gonna write GPU check, CHECK. Yeah, okay, so that's the thing, right? So you are just checking if CUDA is there, right? So essentially what I have in my laptop is an NVIDIA GPU, and NVIDIA developed this programming interface to customize your GPU, right? And the language is called CUDA. You have to learn it separately. It's just nothing, it's just collection of a lot of commands that will help you accelerate your GPU and utilize your GPU, because every computation by default happens on the CPU, right? So the load is diverted to the CPU. But then if you're using by default GPU intensive tasks, right, which by default has to be playing games. So this is essentially in gaming laptop, and I don't have a single game, but irrespective of that matter, the GPU by default only accelerates when you're playing the game. So to make GPU understand that, hey, you know what, I am not playing the game, but I still need you. You need CUDA. Okay, so every time you do AI related task, like we just training a CNN model, the last session you had about clip. So anything for that matter. Okay, and even for now, if you want to do the fine tuning, you have to use CUDA. Okay, so if we are just checking if it is available, so torch, right? So PyTorch is a library. Inside you have the CUDA model. Okay, is available is a function that checks if it's there or not, right? So you can say that CUDA is there because we get CUDA pre-installed in the Google Colab. Okay, so you don't have to do anything. It's just a web interface. You just have to download this file. You just have to keep running it. Okay, so at this point we have the GPU also, which is Tesla T4. Now this is where the things starts getting interesting, isn't it? We have Unsloth. Okay, so if you can see my another screen also, which you can, let me just go to Unsloth. So I keep searching fine tuning. That's why I just searched. Okay, so this is the website that you should hit at. Surprisingly, this entire website is so powerful and at the same time free to use, right? So this is a library essentially, and this website is like, the understanding interface of that. You have to install Unsloth in your notebook in your local laptop using the pip install Unsloth, right? So this website is not a game. It's not a movie or something. It is just a website that talks about the library that you're going to use in your laptop, right? Over here, you can go to the documentation. That's what we are mostly interested at, right? And over here in Unsloth, okay, you have your the GitHub repository. So if you are comfortable with using GitHub, this is the part of your interest. If not, you have the fine tuning guide over here. Okay, and you have the notebooks which I'm using right now. So kind of the notebooks are available here also. But for this session's interest, we are going to go to fine tuning guide, which is available over here also in the getting started page, and as well as over here as well. Okay, you have all the models available which you can download for absolutely free and fine tune them. Okay, these are real models, the real LLM models which were trained by the big techs, which you can utilize in your day-to-day task, or if you are thinking to build up a startup which gives AI services, 100% you can utilize this library. Okay, I'm saying because I do this. So yes, we will be talking about a lot of my personal projects also. I'm not sure at this point if I can show you them, but definitely we can discuss end to end, right? So you're going to have the entire context of fine tuning. At this point, you don't have to read that because there's some reason that I exist here at this point. So for next 1 hour, I'm gonna make your life easy. But after this point, for any reason, okay, obviously you can connect back to me. But for the real reasons, okay, for the real research where people like me learn from, this is the place, right? So you have a lot of code instruction which you can just copy paste, and all the availables are available, all the examples are available here. This is something I would definitely want you to check out. If you want, I can just copy the link of this and send it in the chat, which will help you out in the future purpose, or you can follow along until this session also. So the link has been sent into the chat. Let's go back to our notebook over here. Okay, so give me 1 second. I again lost the thing. Let me reshare. Yes, here we are. Now, okay. Now, at this point, what you're going to use this PyTorch. PyTorch is a library. Okay. Since this session, it's on the practical side, I would love to spend more time on the practical part and explain you this notebook. Okay. So just bear with me. Trust me, it's very easy and very simple. All you need is just awareness of what this syntax means. Like, there is a reason why we use Python for everything in the AI context. You really don't have to learn this language. It's all like you are writing plain English code, right? So I tell to all my students, if you know English, you know Python. Okay. For the majority of you, if you know Python already, it's great. For those who don't understand, it's just that this is a variable, okay, where you are storing your model, right? At this point, I believe you have some understanding about the architecture and the computer science behind it, okay, and the way it stores its memory in the weights, okay, and the way weights are stored, okay. So if this part of understanding is clear, the next of the session is going to be very easy for you. If not, there is a revision that I have planned, okay. So basically, the memory of the LLM is actually stored in the weights, the matrices of 2x2 numbers, right? 2x2 matrices of numbers, okay. These are the weights, okay. Weights, okay, are like in a very simple language, for those who have not understood at this point, if I say something and if my friend says something, okay, we both hold different weightages. Okay, so we can create a dot product of what I say with the weight multiplied by the weight plus what he says with the dot product of the weight that we found out. Okay, and we can come up to a conclusion. Okay, so those are the weights, right? And they are stored in your memory. Okay, they are stored while training in the format of float 64 or float 32. Okay, this is a separate topic that we have today, so we are going to talk about that. We are going to get into the maths as well, so do not worry about that. Okay, but this particular model 5.3 mini, okay, it's an instruct BNB model. Okay, which means that this is very specific to instruction based prompt tuning. We'll talk about this more, right? And it is a 4-bit model, right? So for those who have the computer science background, those who they understood. Okay, for those who not, bits are basically just zeros and ones. Okay, and we can store data in 4 bits. So at this point, I hope you got the idea that we have combinations of 4 bits, zeros and ones. And if you can calculate that, we can come up with maximum 16 such combinations. So we can store 16 numbers in this 4-bit, right? So in that numbers only, all the weights are stored. Basically, that's the meaning of this particular model. So it is relatively lightweight. It is very, very lightweight. Okay, and it is available inside the Unsloth's documentation. So that's what this means. After this, it's very simple. So the max sequence length of the prompt that I'm going to type has to not exceed more than 2048 tokens. Okay, and the data type, we are going to keep it none, because when the computation happens, you might export, you might input, an HTML file, a PDF. You might just write your prompt that is going to be a string data type. Okay, that's the exact reason why we are keeping the data type to be none. Okay, now what we are essentially doing right now is to load the model and the tokenizer. Okay, so we are going to fine tune a model, right? And we need a model. Where is the model? Here it is. Okay, and why do we need a tokenizer? Obviously, because we have to tokenize our inputs. Okay, in a way to give the input, in a way to receive the output. Okay, so we need the tokenizer. Okay, so model and tokenizer both are available in this particular class written in fast language model, which we just imported over here from Unsloth, right? And here you have this method called as from pre-trained. Okay, from pre-trained stands for from the pre-trained model. What are we getting here? Okay, you're getting the model name, which is here. Okay, you're getting the max sequence length, which we just described over here. Okay, data type is going to be this data type, we just described it here, and load in 4-bit, because this is a 4-bit model. So feel free to change this value if you're working with a different model of different bits. Okay, so that information will be available in Unsloth. All you have to just come over here and just like load in 16-bit, load in 8-bit. Okay, so you can just check that and set it equal to true. You have to run this cell. It will run for some time. Okay, and you can see that it consumed 1.84 MBs right over here. With the slight animation, you get this complete loading message that will patch your computer to enable 2x faster free fine tuning. So Olama, sorry, not Olama, Unsloth has connected, okay, and made some changes in the Google's server, which you are right now accessing, right? Because it's happening online, right? At this point, all we need is now data. So at this point, what we have is our model, okay, which is a pre-trained model, which we just took the instruct 4-bit model, and our tokenizer is ready. All we now need is to fine tune, and to fine tune, what we need is our data. Where's the data? We just I just gave you the JSON file. Okay, so that is something that it will not understand. Okay, so we have to change the format. Okay, so from datasets, import dataset. This is a library, okay, that if you're working with data, if you're working as a data engineer, if you're working on a lot of RAG models, LangChain models, agentic models, this library is something of your interest. Okay, you should definitely check it out. All the features that it has, all the functions that it has, is to make your life easy to create your own data set, which you just take from the internet, and to bring it in a nice formatted format. We're going to do that by creating this our own function of format prompt, and we're going to give an example, and that example is coming from user. Okay, so what we are returning to the user is this format of the text. Okay, what we are returning to the user is this format of the text, because guys, the entire the idea of fine tuning is to bring out the customized user experience, right? We can customize how the input goes, how the output looks like. Okay, think about it. At this point, I would like you to give a example. I use DeepSeek a lot. Okay, but the only thing which I do not like about DeepSeek is that it is great. It is actually and that's not something that I don't like about. It is great, that's something I like. That's why I use it. It has very detailed explanation for everything you ask, and sometimes that is a headache. Okay, so if I have a small question to ask, and it is talking about 1000 tokens output it is giving, which is exhausting your token length also, which is bad. You don't want that. And for one simple answer, which AI is supposed to make your life easier, it is actually making it hard by talking too much about it. So now you have to prompt it differently. Answer in 500 words. Answer in 100 words. Answer this, that. Okay. And for someone who is new to using AI, doesn't know all of this, right? Because obviously it is optional, right? But writing a good prompt gives you good output. So what you can do in fine tuning is that you can customize the way the LLM gives an output. It is called as prompt fine tuning, and we will definitely be talking about that in future. Okay. So at the end, what you have is the formatted data stored inside this list coming from this for loop. Okay, from our file. Okay, so we are going to every example that we have out of 500 examples stored in our file. We are going to every example, and we are converting that example into this format, isn't it? And then we are creating our data set from dictionary. Okay, where text is going to be our input, and this is the expected output that we're getting into. Okay, so this is the data set that we just created, and we just stored that in a data set in the variable data set. Technically, Python doesn't work that way. We are referring data set as a keyword reference, but we'll get into that later someday. Now, what is LoRa? LoRa and QLoRa is the topic of the discussion today. Okay, we are going to discuss these fine-tuning techniques in very much detail. Okay, basically at the end of the day, it is basically low order rank adapter, right? Model. Okay, from the same unsloth model dot get PEFT model. PEFT basically stands for efficient fine-tuning, right? Parameter efficient. So what did I do? Parameter efficient fine-tuning. Okay, model. That's what we are going to do. R is the rank size. Okay, this is the LoRa rank. Okay, which we are going to talk about. It is going to give you more capacity. You can all the way rank values from 1 to 8, 16 to 520, something like that. We are here at 64. We can do that. Okay, and these are the mathematical values. Okay, so these are the weight matrices which are denoted in the formula of ChatGPT, DeepSeek, or whatever the model that we were using so far. So these are the mathematical notations which are the parameters that you are which you're interested in. Right, and this is the alpha value, this is the dropout value. So this is where you need high understanding of technical AI architecture, which you have gotten at some point, but to explain it further, that's not the scope of this explanation, so we'll skip this. But in Google Colab you have Gemini integrated, so you can just use this thing and ask Gemini, you know what, explain this code to me. You can do that. I've already run this cell and the model is ready. Okay, at this point, this is the most important part where we are going to use the transformer. Okay, and we are going to use the training arguments. Okay, so this is the training feature. Okay, so trainer is what is going to do the fine tuning for you. Okay, this trainer model, okay, SFTT trainer, okay, is what is going to do the training for you in the fine tuning. Okay, so you are going to customize this entire thing, okay, by your own thing. So you have your model here. Okay, you have run this cell. Okay, so that's why you got in the model. You can see this is the output that we just generated, okay, of 32 layers, right? And we have the tokenizer which we just created, dataset that we just created, text field, dataset text field, which is going to be text because we are going to type in our use case. Okay, and similar way you have all the other arguments. Okay, if you are very interested, I will get into the details, or else it is not needed at this point. When you run this cell, you should get this kind of formatted output where all of the 500 items in your example file are executed, okay, and they are tokenized. At this point, you need the trainer.train module. Okay, so you're going to train your model now. So basically, you're fine-tuning your model now at this point. Okay, so these are the trainer stats. Okay, and when you run this one typical train function, it is going to train your model on your data with these custom instructions. So at this point, in these literally 4 words, okay, in fact, this one word train, the entire fine-tuning is happening. How crazy is that, right? So you can see that these are your training losses all the time. Okay, this is the run history. Okay, the amount of training epochs. So obviously from the first epoch to all the way till the last epoch, we have ran our model. Okay, epoch is nothing but the number of cycles. cycles, right? And at this point, your model is fine-tuned. Okay, training steps per second. So every step for the training took 0.331 second. Okay, and training examples per second. So we dealt with 2.62 examples every second, right? And the total runtime was 571 seconds because it is a relatively small data set and a small model. If you're working with a 1 billion parameter model, if you're working with a 7 billion parameter model, and if you have a lot of data coming from your company, coming from the website that you just scraped, okay, or the fictional data that you just created, it's going to take correlated time. At this time, you just have to test the fine-tuned model. Okay, you can do that by writing a message. Okay, so the message is going to be the role, user, content, and extract the product information. Okay, you can see that this is the exact HTML kind of extracted message that I'm typing over here. Okay, and these are the input tokens that we are typing. Okay, and this is the kind of message that the model is expecting, right? Tokenizer, we are setting it to true. Okay, and we are sending it to CUDA because that's what is at the end of the day going to do every completion for us. Okay, and we are going to generate response by model.generate function. Okay, so generate function is going to generate response for you using the ID input IDs. Okay, the max token limit which you have setting it to 256. So this is what I was telling you about the prompt tuning, right? Because DeepSeek is talking too much and Copilot is talking too less, there is this limited window that you always expect. Okay, so your fine-tuned model will behave, will talk, will respond according to what you code here, right? So you can see that max new tokens are 256. Okay, the caching is going to be true. This will help the model to memorize everything, and similarly you have the other outputs also. And at the end of the day, you can see that the attention mask is not set and cannot be informed. Okay, fine, that is okay. You can see that this is the kind of response that we got. Okay, so you can see that class product. Okay, so you can see that an iPad Air as a product has been extracted. Okay, its price, $1,344 has been extracted. It is in audio category, and it has an assistant feature. Okay, and this is the name of the product that we extracted from one of our examples, which is iPad, its price, its category, its manufacturer, its Dell, and end tag. That's it. Now you may ask me, why is this output so hard to read? Okay, because this is backend going on, right? You are going to now convert this model by running these two cells. So it is going to take relatively much more time. So I will leave it to you. At the end of the day, what you're looking at, yeah. Okay, so at the end of the day, right? So at the end of the day, what you're looking at is a model file like this, which I've already shared with you. Okay, this model file, for this model file, so you're going to use a software development knowledge, or you're going to use another, or you're going to hire another software developer, and you're going to ask me like ask him like, hey, this is the model that I just developed by fine tuning. Now I want you to create an API around this so I can build an application where I can go and interact with it. So that is the end goal. Okay, that's why AI engineers comes into the picture, where they do all the process which I just showed you on the Google Colab in a much precise way and much domain related way. Okay, domain constrained way, domain aligned way. Okay, they collect this model, they do the DevOps part where they deploy this model into AWS, GCP, Vercel, any cloud platform of your interest, right? And they create a fast API. Fast API is a very popular framework. You can obviously use another frameworks also, but that's what the framework of the talk right now. Okay, so you create a fast API which will talk to your web application, which you will develop in HTML, CSS, React, or mobile application. From there, the request that you are typing will be sent through this API to this model. Okay, this model will send the reply. Okay, API will take that and again send it back to your application, and that's where the response will be rendered. That's exactly why the output looks in this way. Okay, so at this point, we have a practical understanding of what fine tuning is, because we have really fine tuned a model with the fictional data, with the model that we took from Unsloth, okay, and the parameters of our own choice, the prompt of our own choice, and the the output token size of our own choice. I saw someone raising the hand. Is it if you have any doubts question, I'm taking right now for 1 minute, 1 to 2 minutes. We'll take some doubts from this code or anything which I said you did not understand. Obviously, we have some explanation coming up, but I saw someone raising the hand. Do we have someone?
So, what kind of data set can be loaded? Can I upload CSV files to this?
Are you talking about the data set, right, which I used?
Yes. Yes.
So it is a JSON data set. Okay. So if you're already able to see my screen, basically JSON is nothing but keys and values in that format. Okay. So this is the format which websites talks to each other. So in that format, you can just use ChatGPT and ask him, right, create a JSON data set for me with 500 examples of of sales data. It will do that for you. That's the same example which I've done here. So it is not made by me actually. I just used AI to build it, and I just saved it as a JSON file. Now that output, that JSON file, we just beautified using the dataset library. That's what we did. So it is not a CSV file.
CSV
It is a
file has to
JSON
be
file.
converted to JSON and that has to be inputted.
It is already JSON. We are going to convert it into the format which the model will understand. For that, we are using the dataset library, and we are customizing our input format. Okay, so that's what is happening there.
No, I was asking if I have a CSV file, then I need to convert it to a JSON format and then feed it.
Yes, you can do that also. You can work with CSV directly also. The dataset of library has all the functions. So yes, you can work with CSV files also. That is perfectly fine. CSV file is perfectly fine.
Okay.
Yeah, because as a AI engineer, right, all your goal is to get the data from multiple sources. So this is the kind of data that you'll scrape from a website. But if you were to go to a CRM, okay, if you were to go to a company's, the database, right? So they are going to send you SQL, format. They're going to send you the CSV format. The sales data, the customer relationship data, right? The CRM data. So all of that is going to come into the CSV picture. So that is also manageable. It is not at all a problem. Excel is a problem. We had to convert Excel into CSV. Yeah. Anyone else who has a doubt, we'll move to the theory session. Yeah. Chaya Ravindra is asking the drive is not accessible. I will figure that out. 1 second. Just give me 1 second. Actually, I have not received your mail itself. Chaya.
You might have got it in updates, I guess.
No, understood. I got it. So many requests are there. So just let me go through there and let me access it to all. Give me 1 second. So 11 people have sent me the request. Okay, and all the 11 people, I'm going to grant you access right now. Done. Okay, folks. So I have so the 11 people who sent the mail request for the drive link which I shared in the chat. I've given you access over 1 hour of time or whatsoever time we are remaining. All of you who are interested in accessing that folder, please hit request through mail. And at the end of the meeting, I will accept all. That's something that we can do for sure. Okay. Now let me run through my slides. All right. So now that we did everything practically, and I have shared the drive with you, which is not very hard to follow, you are able to perform fine tuning. But there were many key parameters. There were many libraries. So Unsloth is a library which I ask you to check out, which you can do that. Okay, but there were internal factors which we did practically, okay, which the library handled for us. So it is perfectly fine if you just understand the code and experiment more with it and experiment more code from Unsloth. You should be able to perform fine tuning on any given model. If you perform fine tuning for roughly, for me, it took me 25 models to fine tune. At this point, I have clear understanding of everything what's inside. So that understanding of code is also more than sufficient, much more than sufficient for you to perform fine tuning of your given task with different type of data set, with different context and the prompting technique, and the different context window and the different model for that matter. But if you want to know what's the maths inside, if you want to know what's the process, if you want to know what is the pipeline that is running behind the code which you just executed, this presentation will help you with that. So this presentation exactly intends to understand the core concepts of transfer learning and why it is revolutionary for NLP, right? So the entire landscape of natural language processing, which is now no more processing, now no one even recognizes it as NLP. It is just like an AI guy talking to us, right? So it has gone into that context, right? And distinguish between fine tuning approaches. So what we use right now was LoRa, okay, and there are other approaches too which are quite helpful. We're going to understand them, okay, and identify how and when to apply fine tuning in real world problems, so you as a working professional can utilize this approach in your day to day life if you were to do that, okay. And this is also very helpful to understand if you are working with a company which is doing it for you, so you have at least some knowledge of what they are doing for you, so you have the knowledge of asking correct questions to them, right? And at the end of the day, we are going to recognize some common pitfalls and the best practices. So in this process, there is a lot that goes wrong, and let me tell you, for those who are Tamilians over here, it is a big talavali, right? And it's basically a big headache, right? You at the end of the day, you just give it up. So it took me, you won't believe, an year to get this to get till this point, but you don't have to give up. It is very easy. That's my understanding at the end of the day, which is what so my goal is, okay. Now the LLM landscape, okay, so this entire presentation, right, is going to be very boring, so other people might have used a very fancy presentation and everything, but my goal is to use this presentation as a whiteboard and to keep me structured in what I talk and to end the session in a given time window, okay. So the LLM landscape, right, basically what I want to show you is that it is just a neural network architecture which is trained on a lot of JSON data. So here is your data, okay, and then you are having another JSON file, okay. What is happening? Just give me 1 second. So where is this, sir? Okay. Okay. The whiteboard is switching actually. Okay, so there's something wrong with the text pack which I'm using. Okay, anyways, you get the idea. So this is something is really long over here. It's okay. So this is the JSON format. Okay, so basically you have these curly braces, you have this colon, you have some text over here, then you have another curly braces, and inside that you have some text. Okay, so that text could be the HTML part or something whatsoever. That is the data that you are feeding to this neural. Okay, the data input. Okay, and the timestamp. Okay, timestamp, right? So this is the way a neural network, okay, a recurrent neural, sorry, a recurrent neural network or the transformer takes the input. Okay, so this is the general idea. Okay, and it calculates all of those, its weights and biases, right? And at the end of the day, at the end of the architecture, actually, what you have is this one function, okay, which predicts the next word. So in the all the connections that you have built over here, something is really wrong. Give me 1 second. If it is very problematic, we'll move to whiteboard. That is also not a problem. Okay. So what you get is a word at the end, right? So in this, what you have are numbers, okay? The numbers which are your weights, okay? And for every neuron, there is a bias associated, okay? Bias, forget this guys, okay? Just focus on the word and what I say, right? So weights and biases are the numbers, which is where the neural network, okay? Any neural network architecture, an LLM stores its memory, okay? So if I say a neural network is smart, a neural network has trained, a neural network has understood, it is basically these weights and biases, okay? And in the context of an LLM, okay, now these are no more numbers, these are no more matrices, now these are vectors, okay, of some values, okay, the vectors. So these are vectors, right? Like this, these are vectors, okay? And they are stored in a vector database, a database which is capable enough to store vectors. So this landscape of the LLM, okay? And this is where our data is. This is what our data is. We are going to touch this data, okay, with this understanding, which we just generated, okay, which we just generated if we were to fine tune a model. And mind you, there are 1 billion such parameter in a very small model, 7 billion, okay, we are now having 500 billion parameters at this point. So even for a big tech company, it is they might do it because they can do anything for they want, but they have already done a generalized task, right? They have already solved a generalized problem by creating ChatGPT, by creating Anthropic, Claude, by creating Google Gemini, by creating Llama by Meta, and by DeepSeek by the Chinese company, right? So they have done their work. Okay, now they don't know what my company does, and they shouldn't know it either. That's exactly why we don't have to play with the entire large language model. All we need is the capability, reasoning capacity of that model, plus our company's data, our personal requirement, okay? And if we were to use this model, if we were to give this model to our customers who are talking to us in a website, and if we were to integrate a chatbot where they are talking about what are our services, what are our working times, what is the query, what is the return policy, okay, any legal queries if they have, everything, okay, on that data, if you want to fine tune this model, okay, you are not interested in touching all these weights and biases. You are not interested to do that. That is not our intention at this point. Okay, so what is it that we do? Okay, what is it that happened under the hood of that code that made the model fine tune? What happened inside the trainer model? That is what we are going to see at this point. Okay, so at this point you are able to understand why exactly transfer learning. Okay, it is for to maintain privacy. Let me just figure out what is wrong with this. Give me 1 second. Okay. Okay, so we have the private data. We'll move to whiteboard after this point. Okay, so let me just actually close this. Okay, and we will just use this draw function over here. We have somewhere draw is there. Okay, 1 second. Huh? Sorry for the delay, guys. Very sorry. I just want things to be very clear. Yeah. We'll just keep it this way. I hope you can see it, right? So, right, in transfer learning, right? Why exactly transfer learning? So already the reason why we are here is that we have understood the idea of transfer learning, right? We are able to understand why it is to, work with your private data. Okay, this private data was never meant to and was never given to this LLM. Okay, this LLM has never seen this data. Okay, so it might have seen the name of your company and probably a little bit in the about section of your website, but it does not know what else you do, right? It does not know what are your privacy policies, what are your hiring policies, what are your product features, core features, what are the other products that you have, what are the offers going on right now. And none of that is known to this LLM. Okay, none of that is known to this LLM, and maybe the data training data cutoff is also there. Okay, training data cutoff is also a thing, right? So maybe if you have updated something in your website, that is definitely not reflected in this LLM, right? So what you're going to do is that take all of your private data, get a data engineer, okay, who will format all the data using the dataset library or with all of his understanding, and okay, he's going to create a dataset for you, right? Create a nice dataset for you in any format, .csv, okay, .json, okay, or .xml, any format for that matter, and then give it to a pre-trained LLM. Okay, and then you're gonna get another AI engineer, okay, to get this pre-trained model, okay, and get this training data to at the end of the day come up with a model which is fine-tuned, okay, to your company, okay, to which is fine-tuned to your company. Okay, now what you're going to do is you're going to deploy this in cloud. The model which we just created can be now deployed in the cloud. Okay, now the backend, now a website can be built. Okay, now a website can be built where you can just input a text. Okay, now this text will go to the cloud. Okay, and then it will send back you the answer. Okay, and which will be displayed over here. So now you can chat with this model. This is the entire idea, and that's exactly why transfer learning has become so popular that every other company, every other, so it's not just talking about companies' website, companies' data, right? I have heard my students who are placed in IT companies, the companies have fine-tuned their model based on the coding, right? So how great is that, right? So a company specific product for a specific tech stack, tech stack that they're using, okay, and they want a AI agent that is going to code for them. So they have really customized the coding models, the code specific models which are out there, which are available. Okay, and they have pre-trained, fine-tuned it based on their company's tech stack, the repositories that they have in their GitHub account, which are which are private to them, all the projects which they might have done in the past, right? All the data they scraped. Okay, they fine-tuned the coding model, like Quen is there. Okay, and they have come up with their own models, and now they are utilizing it every day to boost their productivity. Okay, so these were one of the few examples which I wanted to talk about. Okay, so in this in the landscape of customer service, okay, in the landscape of tech, very specifically programming, okay, even healthcare, okay, to be very specific, drug discovery, okay, and recommendations. This model, this fine tuning is used, right? And these are just one of very few examples. Education, obviously, right? So if I work in a tech company, right? So I can, take all of my company's notes, okay, all of the courses, okay, and fine tune this LLM, okay, on that data. Okay, now the students can come, okay, and directly talk to this LLM and get all the course notes, okay, all the feedbacks, sorry, not feedbacks, all the information about the company, if they want a refund, if they want to pay me, what is the website and everything, okay, are able to get from this LLM. So these are one of very few examples, and the list is, let me tell you, endless. Okay, there is no limit how useful this technique can be. Okay, now pre-training adoption. Okay, so that is what the discussion is right now, right? So what we have at this point is an LLM, okay, which is trained on a lot of data. So text data, okay, HTML, XML data, okay, JSON data, right? Your text data, your PDFs, your Word documents, all of the data, right? All of the data, this LLM is trained on, okay? and it knows about every domain a little bit. It knows about automobile. It knows about medical. Okay, it knows about finance. You name it. It knows it. Okay, but your company is a finance company. You work in Bajaj Finserv, for example. Okay, so now what you need is whatever this model has learned. Okay, so you need those weights and biases. You need them. Okay, and in mathematical notations, it is denoted as delta, this W. Okay, okay. Now with this, what you're going to do is that take your data, which is now mathematically denoted as delta W. We'll talk about this. Okay, and now you apply something to this data set, okay, and fine tune your model. What is that something? We'll talk about it right now. Okay, fine tuning the specialization process. Actually, we just talked about it, like specializing the LLM models and everything. Right now, parameters, types, frozen versus trainable. This is something which is now that you have to understand what gets trained, what gets updated, and what remains is what you need to know in fine tuning and transfer learning. Okay, so in transfer learning, you're transferring your learning from one model to another. So what is that another model? The another model which you just created, which you are just fine tuning. Okay, or your model of your own. It could be anything, right? Or another pre-trained model. So it could be that. Okay, and what is transferring? What is being transferred? These values. Okay, these values are being frozen as it is. Okay, and then they are transferred to another architecture. Right, which you just built. So that's the entire idea of transferring. That's the entire idea of transfer. So what is getting transferred? The weights and biases are frozen. That is the technical word for that. Okay, to keep it as it is. Frozen. Okay, so you take this entire architecture. Okay, you take that entire LLM, you take that entire model. Okay, and you freeze the parameters. Okay, you keep them as it is. Okay, and then you add your external data to the remaining layers. Okay, and then you let the model be update. That is the entire fine tuning idea. Okay, you can also unfreeze the data. You can also not freeze the data. You can also choose to not freeze the data. In that case, if you opt for this, your entire model will update. And that is the idea of full fine tuning. You're fine tuning the entire model itself. That could be a case. Okay, if you have the company resources, if it is for that purpose, say for example, the big techs using the model for programming, it is completely valid for them to do that. Okay, but for your own sweet simple task, or if you're just exploring the AI part, fine tuning part, it is not recommended to do that, right? So in that case, what is something that you will be doing is something that we will discuss right now. Okay, so this is the base model to specialized model, right? So as I said, from all the data, the base LLM is what we call, right? So we just use the instruct 4-bit model. So that is what you call as the base LLM. Okay, base LLM. Okay, and now the data set which I just created for you, the JSON data set. Okay, that is a specialized. That is what you call as a specialized data set. It is specialized in something. Okay, so in our case, it was specialized in customer data. Okay, like actually it was consumer data, so it was having products for customers, actually products for customers. So it was that. Okay, and now you fine tune your model based upon that. So that's what we did, right? And as I said, there are multiple techniques, and these are one of those. You can take a screenshot of this, or if you're using a pen paper, just note it down for you. Okay, so basically out of the multiple types, what I just discussed is a full fine tuning, where you fine tune the entire model itself without freezing any weights and biases. You fine tune the entire model itself, right? Which is great. Now you have the entire model capable of doing what you only want. Okay, the precision is very high, but what comes at the cost is the time taken, the resources exhausted, the amount of data required, because you need lakhs of examples at that point. So a company which has that much of data, which has that of a use case, it is perfectly fine. They will obviously go with that without even touching this entire part. But hey, you know what? Other examples don't exist in this category. they don't, right? So what we need is PEFT. Okay, it is parameter efficient fine tuning. This is what makes the entire game different. Okay, it is basically parameter efficient. What was the problem with full fine tuning? The weights and biases were way too much. That's what your parameters are, right? So the parameters which are, the calculated by the gradient descent model. Okay, the parameters which are calculated by the gradient descent algorithm, which are updated to the local minima. Okay, to reach the maximum precision of the outputs. Those are the learned parameters. Okay, and to redo all of that is another talavali headache, right? And that's exactly why you use parameter efficient fine tuning. So what exactly happens in parameter efficiency? Okay, how do you make your parameters efficient is what the entire game changes. We will talk about that. And RAG is something that you use in your chat GPT. You use this every day. Okay, retrieval augmented generation. Okay, so you're going to retrieve from the augmented data which you just passed as a PDF in your chat GPT, and it will generate text for that. So that is what is happening, right? So you're using your chat GPT, you're using your DeepSeek, right? You're using your Microsoft Copilot in your laptop, right? You're using other model, you're using Grok, right? So you're passing PDFs to it. So that's what is the idea of RAG. What we did right now was LoRa. And in future, if you were to do fine tuning, you will be using one of these two techniques only. And prompt tuning, which we just did inside along with the LoRa. So our goal is to understand LoRa and QLoRa very well. Okay. So I'm extremely sorry for a very simple presentation, but I thought like the understanding is more important. So I focused on that. So I focused upon the structure of this session and the which I found on internet. My apologies if you were expecting a very beautiful presentation. I could not bring you that, right? So if we were to meet next time, probably I'll work upon that. Okay. So that's the thing, right? Full tuning. Okay, where you have the entire massive data set. Okay, quick revision. Okay, you train your model, you calculate the gradients. Okay, by del loss, by the del function loss. Okay, so this is the derivatives that you calculate, and you apply a chain rule. Okay, where you just go back all the way till the endpoint where you got your input. Okay, and you update those weights and basically your parameters. Right, so you update that using this one chain rule, okay, multiplied by a learning rate. Okay, so we don't have to get into that much of maths. Basically, if you are interested, you can read the research paper of gradient descent algorithm. Okay, and now this is where your base model is generated, say for example GPT-3, okay, or Claude. Now you fine tune it with the domain specific data that you just came up with, for example the data which I provided you in the drive. Okay, and you fine tune your LLM with that data. So your entire weights and biases, entire parameters are now changed to the data what you gave. So obviously the performance of the LLM on what it knew before will degrade, which is fine because that model is still available somewhere else in the chat GPT app or somewhere, right? Or another copy of that is available. You can still use that. Okay, but all you wanted is for your own domain specificity, which is now successfully achieved. Okay, so now a user can interact with the model. I also gave you some sort of software development perspective of how that could happen, right? So you just have to deploy it in the cloud, like AWS server or something. Okay, you have to just build an API. Okay, which will talk to this model. Okay, so your user is basically going to send the query. Okay, it will be sent to the model. Model will send the response back to the API. API will give the response back to the user. User means like your browser or the website, web app, or any phone application, right? So that is the entire idea of full fine tuning, but you don't do that. Okay, so domain specific fine tuning, task specific fine tuning. Okay, so this is what we actually prefer. We don't prefer fine tuning for most of the use cases. Okay, so what's the next solution? Okay, so what are the challenges? All the weights and biases must be updated. Okay, hardware resource constraints are there. Okay, and along with that, what is another headache is that you have a lot of downstream tasks. So as I was explaining you have to retrain the entire, fine-tune the entire model which is there. Okay, the computation, the expertise, the proper amount of code which is required, that is there. but now you have to redeploy the model. The model will drift, which means the performance will degrade for the entire models because you haven't frozen them. Okay, by someone. Okay, the model will drift. Even a simple machine learning model may drift. Okay, so it's a large language model. You have to monitor it. You have to keep inferencing from it. You have to keep evolving it. Okay, there are other documentations, other things are there. So all of that downstream tasks are there. Okay, so that's exactly why we don't go for fine tuning. But obviously, if that is what you need, you will definitely go for it. You will not consider any of this, right? So what's the next solution, right? LoRa and QLoRa. Okay, so that is the solution, LoRa and QLoRa. Okay, so these are the transfer learning basics which I just showed you. Okay, so this is the image which I came up with later. You have a pre-trained model. Okay, you have a pre-trained model. Okay, you have a pre-trained model. Okay, so this is the CNN model. For that perspective, we are talking about LLM. So this entirely architecture is totally different for you. But just get the idea that the layers as a concept is still there. Okay, the encoder decoder basically has layers inside. Okay, which stores the values of parameters in their nodes, right? And that's what is being transferred. Okay, so which is there. Now, what is PEFT, right? What is PEFT? So that's what we now have to talk about. Okay, it is parameter efficient. I guess someone's mic is turned on. Fine tuning. Okay, it stands for parameter efficient fine tuning. Now, what you do is apply a beautiful piece of maths. Okay, now you have to understand how the memory is there of an LLM. Okay, those are basically the parameters. Okay, and they are either vectors or matrices. Okay, for most practical cases, they are matrices. Right, the data comes in vectors, obviously. Right, these are parameters are matrices. Now, what you do is you optimize these weights. Okay, these are your parameters, right? And these parameters are actually stored in float 32 data type. Okay, float 32 data type. So it stores data with 32 bits precision in that way. Okay, so the parameter value can look like 1.378. Okay, it can look like 0.829 like that. So a lot of precision is there. That's why these models are so good, because the values are precisely stored. But you are running that on your local server, okay, or your server which you are paying for, where you pay for the load and which you obviously want to ready. So you optimize model. Okay, and when I say you want to optimize your model, you're talking about optimizing these parameters. So that's what you're talking, right? You're talking about optimizing these numbers. And the simple way to do that is basically typecasting. A simple typecasting is what you do. Okay, this typecasting is what you call as quantization. This is one method. The another method would be using matrix decomposition. Okay, the another method could be matrix decomposition. So what you're going to do is you are going to take this matrix and decompose it into ranks. Okay, decompose this into ranks. So say, for example, if I have a matrix which looks like this. Just a random numbers. Okay, so you are going to get a rank like this. So this is basically the decomposition of this matrix into a rank 1. Okay, the rank 2 could look like this. Right, this is the rank 2. So you optimize your matrices this way, and obviously at this point you can see that you are using lesser data. So this is where you are saving your weights and biases. Okay, right, matrix decomposition, this is second way, and this is what goes on in LoRa. Okay, because if you see, LoRa stands for lower order rank adoption. Okay, It stands for lower order rank adoption. And folks, this is what we used in our fine tuning example in Google Colab. Okay, so if you go back to the code, now you will relate that we were actually using LoRa. Okay, so we were using LoRa, which was taking the the parameters of the fine-tuned model and the parameters that you are going to learn, okay, and reduce the rank order of it. And with that reduced rank, okay, with that reduced rank, we track the changes instead of we updating all the weights. We track the changes using the rank values, and the approach is matrix decomposition, as I just said. Okay, so this is the maths behind LoRa. Okay, so the W naught, which I just said, so I have already scribbled over here. Oh no, it's actually the image, right? So this is the matrix, n cross n matrix. Okay, so it could be 3 cross 3. Okay, it could be n cross n, right? So this is the matrix which is your primary parameter coming from your model, okay, which is available because the model is now open source. I was seeing in the past session, the previous trainer was telling you about the open source models, okay, and in what way they are open source. Is the entire code available to you? Is the data which it was trained available to you, or are just the weights and biases, the parameters are available to you? So these are the only 3 ways where a model can be provided to you. Or the 4th way is the closed model. You just have to pay for the API, right? Or you have to pay for the application which uses the model's API. Okay, so what we need is the parameter. So we need the true open source nature of the model to work on fine tuning, or else it is not possible. Or else it is not possible, right? So this is your W naught. You freeze it. Yeah, you freeze it. Okay, you freeze it. You don't touch it. You don't touch it. You freeze it, right? What you typically do is you have your another data, right, where you are having your matrices calculated now, and you change its rank order to a lower rank. Okay, and that rank order is obviously going to be lesser than what this n is, right? Because what's the point of going with the same rank? We would end up with the same amount of weights and our end goal was to reduce the weights and biases in order to optimize the computation and the amount of data, right? In the data, what I mean by is the parameters that we have, right? So that's what you do by the lower rank part, okay? And the A stands for this matrix and the B stands for this matrix, right? So this is basically nothing but the dot product, which you get, so if you have n cross m and m cross n, this is the requirement for the dot product. Basic maths, right? And the resultant shape of your matrix would be n cross n. Okay, so if this was a 3 cross 2 cross 2 cross 3 model, okay, the resultant shape would be 3 cross 3. Okay, or vice versa, 2 cross 2. So that is the entire idea, right? That is the entire idea. Okay, so that's what happens here. So this is the math. If you are interested, definitely now this time frame will not allow us to do that. Okay, is it already time? What time is the session about to get supposed to get over? 9 o'clock, right? Is it, or 9:30? Is it? I'm sorry. So I guess we have very less time, guys. I'm
9.
yeah,
Up to 9 o'clock.
9. Okay, up to 9 o'clock. Okay. I'm very sorry if I have bored you enough, but this is the complete idea because the major part in the code we just did it, and as well it will be shared with you. Okay, so these are the trainable parameters of LoRa. Okay, so whatever the rank that you go with. So if you go back to the code which we were using, okay, we are actually almost there. We'll cover everything, right? If you see the code now, you will see me using the rank 16. You will see me using the rank 16. So whatsoever parameter that you go with, you have 7 billion, 13 billion, 70 billion, 180 billion. You have more parameters also, but those are not open source. If they are, you can just do the calculation, right? And according to given rank order, these are the number of trainable parameters. So there are trainable parameters, there are frozen parameters, right? The parameters that are trainable parameters, and then there are frozen parameters. Right, there are trainable parameters and then there are frozen parameters. So that's what it is, right? So this is the tabular chart which will give you the very good idea about how the thing goes. Okay, now QLoRa. Okay, this is the step 2. Okay, this is the the version 2.0 of LoRa. What you do is obviously you decompose your matrix, but the internal data type also you change. Okay, so the internal data type also you change. So if you were to talk about the maths behind this, so you have to go back to your computer science topics, and you have to just refer how every data type stores data in bits. Okay, so you have to study. So basically, you have to see. All of you know that obviously. That's an assumption before using this. The data types as int 8. This is what our target is. Okay, so we bring our model from float 32 to int 8. Now you will say that there is an information loss. Which is true. Okay, you are storing models, you are storing your weights in this precision, say for example. Okay, and now you're converting that to 2. So obviously the precision value is being lost, which is there, which is agreeable. But fine, hey, you know, our end goal is to fine tune the model, not to go with the entire model. So we are perfectly fine with touching the other parameters. At the end of the day, what is the model understanding my data is what my entire goal is, right? So that is what is happening here, right? But what is quantization? As I just explained you, the parameters of LLMs are stored in float 32 bits. Okay, we convert the data type into int 8. So that's what we do. Okay, and this is the PEFT architecture, right? So in the PEFT architecture, we have the standard LLM that stores the data into the state of 32 bits. Okay, and then the model pre-trained is in 18 bits. Okay, this is the LoRa where we are having the adapter layers that works on the rank values. Okay, and this is the Q LoRa where we optimize the values inside that rank also. Okay, is someone having question or is it a mic on? Okay, now this is something that I have practically showed you. Okay, the prompt tuning where you can prompt tuning is ideal when you are having a large pre-trained model like 3 billion plus. Okay, the training data is limited and all you want is to customize the behavior of how you interact with the model and how the model responds back to you. That is all prompt tuning. Okay, so prompt tuning is nothing but it's a very simple process of just the interaction is changed. You are not touching the parameters at the at the end of the day here. You're not doing freezing, you're not doing LoRa, you're not doing Q LoRa, you're not doing quantization, you're not doing matrix decomposition, you're not doing fine tuning itself. Actually, what you're doing is prompt tuning, right? You're changing the way how this model is going to talk to you, how the model is going to respond back to you, and the parameters also were discussed back in the code, right? So the amount of response token, okay, the format that is expected as an input. So all of those things can be changed. Okay, the GPU memory constraint and everything of that sort, right? So you can just take a screenshot or read through it. Okay, then there is one more type of fine tuning. So we talked about track, which you are already doing. Okay, we talked about full tuning, which I said the big text or the one big requirement would satisfy. LoRa and Q LoRa, which is the most of the cases we practically did LoRa and we mathematically discussed LoRa and Q LoRa. Okay, and there is one more thing which I have to talk about. It is instruction tuning and task specific tuning. Okay, now in a nutshell, basically instruction tuning, as the method says, okay, this method focuses on teaching models to follow diverse natural instructions, enhancing their ability to understand and respond to various tasks. I'll give you an example. So when ChatGPT came for the first time, as in the application, which was using the GPT-3, which, if I'm not wrong, because that's when it was quite popular, it was hard for them to interact with it. Okay, like they were just talking it like, and they were influencers talking about you have to put colons, quotes, and everything inside the prompt. Okay, so there was a lot of confusion. I do remember one of my colleague asking me, "Hey, how to use ChatGPT?" And I was amazed. Like, it's like you know, it's like teaching your old grandparents how to use YouTube, right? So it is just that basically. You just know where you just need to know where your the buttons and inputs are, where to put file and everything. That's all about it. You don't have to learn how to use ChatGPT. But even if you were to use it in a day-to-day life, the way that you would get the response back was frustrating. Okay, and in most of the cases. So what they did was, and people were not very good at English, maximum of the people, if you talk about the Indian context. Okay, so the way we write prompt, we have spelling errors, right? We have the function, this formation error. So if you were not to speak grammatically correct, okay, the you contradict the entire idea of NLP. if we see when I teach NLP, and if we talk about NLP, natural language processing, tech is there, AI is there, RNNs, LLMs are there. But one more thing that you have to learn and utilize and implement is the linguistics. You have to learn what is the grammatical formation of that language which you're working upon. You have to know what are the stop words. You have to know what is necessary, what is not necessary. You need to know what format structure means what are the past tenses, future tenses. The entire linguistics has to be studied. Okay. And if you were to just prompt in a incorrect way of your own thinking, right? It is not going to give you the output of your expectation. So this is where you fine tune your model on the basis of instructions. So hey, you know what? This kind of instructions may mean this. Okay, so there is a way that using a JSON format you can change that, right? It is particularly effective for tasks requiring clear guidance and step-by-step reasoning. Okay, so if I were to ask, hey, you know what? These are my PDFs, and generate a note for me, generate notes for me. So what will the instruction tuning look like? The instruction tuning would look like: get the data, extract the text, vectorize it, take the vectors, take all the chapter bulleting points. Okay, take all the inputs, take all the notes from the summarize all the big paragraphs. Okay, keep images if you are working with the image model also, and so on, so on, so on, so right. So this is the entire format. So every time you hit that prompt, right, in whatsoever way, okay, the response of the LLM is going to look the same, and it is going to be impressive because at the end of the day that's what you're expecting. So this is instruction tuning. Okay, and task specific tuning is what the approach involves further training a pre-trained model on a smaller task specific dataset to adopt it for a particular task or domain, which is where you can use either fine tuning, full fine tuning, LoRa, QLoRa, or adaptive layers. Okay, so this is the entire thing. The aim is to optimize models performance on specific applications and degrade on what was it meant to do for. Okay, so this is the unhidden definition, right? It will degrade the performance on what it was able to do. It will increase the performance on now what you are expecting it to do, which is at the end of the day what you want. Okay, so this is the PEFT comparison, right? So you have full fine tuning, you have LoRa, you have QLoRa, you have adapter, and you have the prompt tuning. And the trainable parameters in full fine tuning is obviously you're working with the entire weights and biases. Okay, and that's where you're going to exhaust all your 100% parameters. Whereas in LoRa and QLoRa, you're only going to freeze the entire parameters. Okay, you're going to freeze the entire thing. And what you're going to do now is that what you have is a new matrix and you're going to decompose it. And in QLoRa, the internal values of that decomposed matrix, you are going to quantize it. Okay, and then feed forward, then do the feed forward propagation and then the back propagation. I hope you get the idea from the previous LLM classes. And then the model is going to be updated. Now with these, newly learned values, your model is going to respond in a way that you like it to do so. Okay, and obviously the prompting techniques are there which will enhance it even further. And since it is prompting just a simple thing, okay, it is going to use the lowest number of memory usage and training parameters. Okay, and you can see the performance of the fully fine-tuned model is going to be the best because you have completely customized the entire model end to end based on what you want it to do. So it is going to be the flawless model if it were to do the coding task. It would be the most flawless model if it was to work on the healthcare data, education data. So it is great if you want to do that. But if not, okay, LoRa and QLoRa are still not that bad. Okay, it is just 95 to 99% of what a fully fine-tuned model would return back. Okay, and prompt tuning, it is basically the user experience, what you're expecting, what you're focusing at, right? And this is the entire model summary, methods summary. You can take a screenshot of this. This is like the entire entire summary of this entire session, 1.5 hour session. Where prompt engineering, right, is basically prompt tuning, right? So it is basically simple task adoption where you test the ideas. Okay, just no need of data actually. It is just prompt tuning. You are just customizing the way the prompts are given and they are returned back, right? And this is the summary, right? So if we have already talked about it, I want you to take a screenshot. I'll give you 10 seconds for that. And at this point we are mostly done. So what we have is the applications. Okay, so LoRa and QLoRa could be used for the general purpose. This is the best balance, right? The adapter layers are when you need the layer specific control. So you fine tune those layers. So this is more on a technical side. Prompt tuning is when you want the user experience and the response to be better, and fully fine tuning only when you need a massive task specific data and the resource are available. Okay. Data preparation strategies is something which we really need to talk about, because the fine tuning wouldn't have worked. It's very great. One of the gentlemen asked the question about if they had CSV data, right? So it really does matter what kind of data that you provide. You cannot give any kind of data. Okay. So the standardization, normalization, that has to be there. Okay. So you need database engineers, you need data engineers, right, to get the right shape of data. Okay. Hyperparameter confusion, the rank size, which quantization value are you going to go with? Okay, these are the hyperparameters which are in your control. Okay, the output size tokens. So there were many hyperparameters which even I coded. Okay, so when you go back to the Google Colab, you will understand these things better. Evaluation matrices, what to use. Okay. So that is the thing. Okay. And these are the common pitfalls, right? So data starvation, right? The lack of data that you provide. Okay. Catastrophic forgetting, right? So one more session is going to come from my side for you. Actually, that is about hallucinations. That's where we are going to talk a few topics from this slide. At this point, it is very self-explanatory. Memory issues, out of memory errors on the 9th point and everything. I would want you to take a screenshot of this, right? It is self-explanatory. The boring maths part is explained, the coding part is explained, and then this is the entire pipeline, guys. Right? So folks, this was fine tuning an LLM and transferring the knowledge of one LLM to another. I hope I was able to, summarize my understanding of so far whatsoever I have understood, and you were able to grasp something out of it. Right? If you have any questions, I'm taking them right now, or else we are good to wind up. Thank you. Thank you so much at this point.
Any questions from the participants? You can post it in the chat box.
Yeah, I'm reading the chats now. Thank you. Thank you so much, people. So to compare two document versions, which LLM and how can it be used? So Savita, the thing is, that is a very general task. You can just use an existing application, and basically it falls under the RAG category. So you need to retrieve the augmented data, which are the two documents that you're talking about. So just upload them in ChatGPT. It's better if the documents are named differently, because it treats that also. And then it is going to give you the feedback of how these documents are different, what are the differences and everything.
Sir, sir, I just wanted to know, with research perspective, how can
Yes.
we go ahead with this topic?
With research perspective, right? So what you can have is the findings, the citations, the research papers of what you already have. So you're mostly talking about the textual data. So you need to get some person, or you need to get the automated code pipeline from ChatGPT DeepSeek to convert all of your documentation into a one single PDF, which is very big, or chunks of PDFs. So that is now your data. This is the first step, the data. So now what you have is data, and now you can go with QLoRa, and you can use my code. Okay, and you can find in Unsloth website which whatever the model suits the research perspective. Okay, now what you're looking at over here is the reasoning capacity of the model. Okay, and Unsloth has very good documentation of every model, what it is good at. Okay, so you just replace the model name in the code which I gave you. Okay, you replace the data which I gave you, and obviously need some more tweaks here and there also. At the end of the day, you will get a model which is fine-tuned, which is now able to research along with you or for you. Now you need to convert that into an application with a software developer. Okay, and at that point you can talk to that LLM, you can talk to that model in the whatever the domain that you are researching in. Now that model has capability of reasoning on the behalf of you or for you or along with you. So that's how it is going to help you.
Okay, sir.
What's
Thank
the
you,
best?
sir.
Thank you so much. What's the best format to create data set? JSON and CSV, the best format. Thank you, Chaya. The documents you shared for LLM is good to start. Yeah. It is good to start with. How can we create data set from book or set of research paper for fine tuning? You have to scan it, convert it to PDF, and that's it. You're good to go. Thank you so much. If you understood it very well. Thank you so much. Yeah. Are you having more questions or we are good to wind up?
Any more questions?
Oh, so you want this PPT? I thought like this is going to be the worst PPT of all time. Definitely, I'll put this PPT up. We'll share it with the organizer. Okay, then we can give complete book as it for fine tuning or in the question and answer format. No, you can give the complete book, but it has to be formatted. So chapter wise, it has to be formatted. That is the way, or else it will fall under the rack category. So most of the questions that I'm getting into the chat are falling under the rack category, except the research part. So you can use DeepSeek. Really, it has a bigger context window. It has a better response window, and it has better input window. So I guess up to 50 MB of scanned document you can upload in DeepSeek. So please use DeepSeek if you want anything related to RAG applications. That is something I use a lot, and it is very, very effective. I guess we are done with the questions.
Yes, we are done.
Yeah. Okay.
Thank you so much, sir.
Thank you so
I
much.
appreciate your time and the knowledge that you shared with us. It was really a very informative session. I hope you all make a good use of it in our future research. Thank you so much for being with us, sir.
Thank you so much. Yeah.
To all the participants, immediately after the session, we'll be sharing the feedback link and quiz for today. Kindly attend it. Thank you all. Meet you tomorrow.
There's one last question I'll answer and go. Using local LLMs for Olama Gamma model is good for. That's good. Pragya Nandan. Yeah, you can go for it. There's a lot of content available on Olama. You can definitely check it out, or someday later if you want, we can of course discuss through the organizers or anything. Thank you so much. Okay, thank you so much. We'll wind up now. Shall I leave?
Yes, sir. Thank you.
Thank you so much.
Thanks.
Thank you, sir.
Somebody is asking for email ID.